All right, thank you everybody. Thanks for joining us this year at the 2022 Senior Project Lab Project Symposium. We are excited to be here again this year. This year we have a live audience, so it's back to normal, I guess. We've survived COVID, and we're here to show what our students have to present and what they have done in the last 300 to 400 hours in 6 months or so. So we're really excited. We have the luxury of streaming this year too, so we got really good feedback in the last couple of years for the stream, the access to the stream. So many of our outside interested parties have said that they don't have the time necessarily to commit to 4 days of being here, but this gave us a lot of versatility to be able to watch additional time that they may not have been able to do in the past. So I'm not going to delay too much. We're going to start right away. We're going to start with Andrew, and Andrew Jardine has his wireless alarm system that he's going to talk about. Andrew, anytime.
All right. Going first, no pressure. All right, hi. I'm Andrew Jardine. I'm an electronics engineering technology student here at NBCC Moncton. And my project for the Senior Symposium is the wireless alarm system. For my presentation, I'm going to cover the planning, the design, the programming, and the construction of the project. So what is it and why did I decide to build it? I'm going to go over the costs, the functional overview and the block diagram, the electronic schematic, PCB design, the software and the system flow, as well as testing and analysis before giving my feedback on what I learned from the overall project. So, excuse me. So I chose to do my project mainly to further my education. That's why we're here at the school, which is to learn more about the field we've chosen. I wanted to improve some my skills in a few key areas, and programming was one of them. Due to the recent increase in crime in the Moncton area, the idea for the wireless alarm system was born. And it's basically a way to solve a problem, as one of our instructors so often likes to put it. Programming is a way to solve a problem. According to Stats Canada, in 2018, Moncton saw an occurrence of property crime per 100,000 people 65% higher than New Brunswick overall, and 50% higher than that of Canada. That includes Toronto. So it's not a great statistic. So a wireless alarm system would be overall a wise investment for a homeowner. Due to the increases in home security offerings that come with attached monthly fees, the DIY market is actually a fantastic alternative for people who would like to protect their stuff but don't really want to go broke while doing it. So, for my costs, the entire project costs $409.89, not including the government cut. What did I get for $410? Besides a lot of sleepless nights and some program management experience? Well, I'd like to show you. So, laser pointer here. The functional overview is briefly going to cover the top level workings of the system and how the major components interact with each other. So the wireless alarm system is powered by a 120 volt AC wall adapter. It also has a backup power supply consisting of a non-rechargeable 9 volt battery. Both of these feed into the reverse polarity protection circuit. From there, they split off into the audible alert, which due to the construction of the buzzer, it requires a higher voltage level in order to produce a significantly loud sound. It won't deafen anybody, but it will definitely keep you awake. These power inputs are regulated down to 5 volts to power the majority components of the system, including the microcontroller and the 16:2 LCD screen. However, the voltage regulator, or rather, sorry, getting ahead of sorts. The wireless receiver module actually requires further regulation for 3.3 volts in order to properly communicate and prevent damage due to overvoltage. Communication from the door contacts is actually handled by this wireless module, which passes the line state of the reed switch, more on him later, through the wireless transmitter module to the receiver, then to the microcontroller, which responds to the various line states based on its programming and the behavior state that it's in. The user can move between the modes via input on the 4x4 keypad and allows them to enter the different modes and arm and disarm the system. So, with the rough structure covered, we'll go over the electronics schematic to show how the various components interact with each other on a hardware level. So we'll start with the door contact sensors. The door contact sensors are powered by a pair of CR2025 or CR2032 batteries. Due to current limitations, I actually switched to 2032s after a recent test over this past week. Unfortunately, it was after the Symposium drawing packages were due. C5 over here is our decoupling capacitor, which separates our voltage from the system ground. Over here we have R1, which is simply a pull-up resistor and pulls the system up to 5 volts. Down here is sort of, it's a basic switch, but rather than working on a press principle to close the circuit, it actually works based on proximity of a magnet. So once a magnet of sufficient strength is brought nearby, the two filaments you see inside are actually attracted to one another and close the switch, pulling the circuit low, which is what triggers the circuit to communicate with the master module. JP1 through JP8 are a set of soldered jumper points, and they were actually brought in for 2 specific reasons. Number one is because due to the configuration of the XB modules and the way they communicate with one another, this allowed me to troubleshoot and reorganize the system without losing an entire module if a pin happened to be damaged or programming on one of the pins did not respond. So JP1 on this particular unit is the one that is bridged. However, on the secondary door sensor, it's actually JP2 because of something called line passing, which is what I'll cover next. So U3 is the XB module. They have, as I said, they have a feature called line passing, which allows a one-to-one communication between the devices. End devices in XB module networks can actually be configured to either receive input and transmit it to the receiver module, or they can receive said input and output it on the pins. But it is a one-to-one pin configuration. So pin 0 is connected to pin 0 on the receiver module, pin 1 is connected to pin 1. So the reason for the jumper is if pin 0 gets broken, I don't have a completely worthless module. I could resolder jumper 2, jumper 3, or jumper 4, and now my module is back in action with minimal fuss. So, onto the main board, we've got our voltage regulation and protection circuit. It's actually, the main unit is actually powered by, as I said, 120 volt AC wall adapter, which is regulated down to 12 volts. That's plugged into J1, which is a 2.1 by 5 millimeter barrel jack. It can also be powered by the 9-volt backup battery unit. Both of these are connected to a pair of Schottky diodes with a low forward voltage. This minimizes power losses to the system. The entire system only draws about 55 milliamps at 12 volts. So the power supply is more than enough to power the entire circuit. Q1 was my original reverse voltage protection before I had incorporated the backup battery. And it's a P-channel MOSFET that, when connected the right way around, allows for the circuit to be powered. Excuse me. So the voltage regulation is handled by the LM7805, and the entire reason for choosing this was because they're extremely common, very reliable, ubiquitous IC, and they need very minimal additional components in order to ensure that the transient response and the input voltage are stable. A simple pair of capacitors handles pretty much everything that's needed to go along with the circuit. On the other side of the 5-volt regulator, feeding out to VCC is the main power line for the entire circuit. It also feeds, the LD11117AV33, which is a 3.3 volt regulated low dropout regulator. The only thing this is responsible for is providing power to the XB module. Everything else on the circuit runs on 5 volts. And again, it requires minimal additional components in order to have a stable voltage output. So, user input and feedback for the system. The user input is handled by KP1, which is a 4x4 matrix keypad in a telephone pad configuration, with the addition of A through D down the side. These are allow the user to select the individual modes based on the pin readings for U1 or from U1, my Atmega 328P microcontroller over here. KP1 is actually connected via a ribbon cable. It's mounted directly on the front of the unit instead of mounted directly on the board, and it is read by port B on the microcontroller interface. Up here we have the decoupling capacitor for our main microcontroller, and down here we have our in-circuit serial programmer, which allows the programming to be updated or changed as needed as the project develops. R2 is there between pin 1, our reset pin, and pin 7, the VCC, due to the configuration and the requirements of the PIC-Kit 4, which is used to program this project. All right, over on the user feedback side, we have BZ1, which is our piezo buzzer. It's powered by 12 volts, and it's a 24 millimeter piezo buzzer system. The switch controlling the buzzer in this case is Q2, which is an N-channel MOSFET in enhancement mode, which is currently pulled low currently pulled into the cutoff region by the pull-down resistor. If given 5 volts from PC3, it will allow the MOSFET to conduct and puts out about 90 dB. The entire buzzer rather can go up to about 100 dB with 15 volts. I was working next to this for about 400 hours and I didn't want to be deaf by the end of the project, so it was limited. The rest of the user feedback is actually handled by DS1, which is a 16:2 tricolor backlight LCD screen, which communicates with U1, our microcontroller, by two-wire interface, or I2C, depending if you want to pay the royalties in using the terminology or not. R4 through R6 down here are simply current limiting resistors for the backlight. The values were chosen there to limit the current to 5 milliamps below the maximum allowed for that particular lead. And as you can see, the red actually requires a larger resistor due to the construction of the circuit. There we go. So our final component communicating with U1 is our XB receiver module. Over here we've got our decoupling capacitor, P10, J10, J11, P11 are pin and socket connectors used with all the XB modules across both boards in this system. Those were sort of a safety that I added in case, due to the construction of the board, it interfered with the wireless signal of the XB module. So that would allow me to remove it and place it elsewhere and run ribbon cables. Not the ideal solution, but this is all about learning, and that is the route I chose for these. They're also rather expensive modules, so I may want them back at the end of the project. R7 through R14 are simply pull-down resistors used for the communication lines, D0 through D, it's actually 14, they're out of sequence due to the construction of the XB modules, and they are connected to port D to communicate various states of the attached or connected door contact sensors. So, PCB design for the main board. This was actually a really interesting part of the design process because due to the nature of the components and especially the XB modules, there were a lot of considerations that had to be taken into account. As I was told during the process, PCB board design is almost half art and half science. You have to ensure your traces are far enough apart to not interfere with each other. But if, like my initial design, they're kind of haphazard, it looks very ugly, and it does not necessarily work well with the overall function of the board. So, as you can see right here, my ground plane stops, and that is actually due to a requirement in the use of the XB modules that has is an 84 millimeter by 16 millimeter keep out zone, that nothing metallic can be in it. As you can see, the screw holes are even down here just to keep them well outside of that exclusion zone. It was also pointed out during my first iteration where I did not have an upper bound, I actually did not have the PCB there at all, that it was not a great idea as it would likely lead to damage to the XB module just having an overhang like that. So this went through about 10 iterations before it was finally sent off to the board house. On the board house side of things, as most of you know, we were given the option of doing it in-house through photolithography, can't say that today, or farming it out to a board house for a sort of more professional look to it. If I go farther in my career in board design, I wanted the experience of having to deal with someone on the other end that I don't have immediate access to, and what I send them is what I get back, whether or not it is correct or not. So great care had to be taken to follow not only the component design requirements, but the board house design requirements as well. they have very few forgivings on their design requirements, and if you get them wrong, it just delays your board and makes it take even longer to get produced. The most nerve-wracking aspect of the board design wasn't the design itself, it was sending it out and waiting for it to come back. The shipping dates turned out to be a little bit strange. It came in a little earlier, but even still, if I found an error after I sent this board out, I wouldn't have time to send a second iteration out to be redone if I found some major errors. There were a few errors discovered in the process of testing the board, but they were corrected without too much overall fuss. So PC sensor board PCB rather, is more or less the same principle. Over here you can see the solder jumpers, and there's nothing overall special about that. Just add on a little bit more solder and drag your soldering iron to ensure that they're closed. There's no extra little fiddly bits to get lost or fall off your project once it's in the enclosure. And again, over here you can see that the exclusion zone is still there, and I tried to minimize the interaction with the screws. Although due to the size of the enclosure, it wasn't completely successful. So, this is the major part of my project here. As you can tell, most of my project is design. It revolves around the software end of things. I've got about 1,300 lines of code, all told at the end of the day. And so I'll take you through a rough overview of the way the code actually interacts. The program is set up as a state machine, which is very similar to the way a traffic light operates. Each state has their own operational criteria that they either ignore certain inputs or behave in a specific manner associated with those inputs. For example, in disarm status up here, if I press 1 through 0, 0 through 9, I guess, the digit is loaded into the pin pad array, the password array rather. Whereas over here in the change chimes function, it would actually be used to choose whether the front door sensor or the back door sensor is the exclusive sensor to allow the user to enter or leave the area without immediately triggering the alarm. These pieces right here that look like home plates actually refer to sections of the flowchart that are on other pages. Trying to fit the entire flowchart for my code on one page is not feasible and being able to be read. So when the system starts up, it actually starts up in disarm status, and it waits for keypad presses. As the keypads are pressed, it will wait until it is a fully loaded pin pad array. Once the pin has 4 digits contained within it, the first thing it will do is check to ensure the pin is correct. If it does not match the master pin, it exits and returns to disarm status and erases the pin for you to try again. Then it will go through the various mode selections to see which option was chosen. If option A was chosen, it will change to allow you to change chimes and go to the change chimes function. The change chimes function in this case is what you saw me demonstrating earlier, turning the chimes on and off. Anytime the door is opened in the disarm status, it will sound unless I've turned it off. In this case I have. There's no beep because it was told to be silent. Excuse me. If option B is chosen, the system will change to grace period, which will allow the user to change the entry and exit delay timer. So once the alarm has been set, it triggers a timer, and you have 15, 20, up to 120 seconds to exit the area without triggering the alarm. After that period has expired, the alarm is set, and any entry into the area will either set off the alarm if you pick one of the other doors, or if you enter through your chosen door, the countdown will begin. The countdown again gives you about 20 to 120 seconds, depending on what you've entered, of time to enter in the master pin and disable the impending alarm. Option C allows you to change the master pin for the entire system. It's currently set to 9876. And option D will allow you to change the door that is used to enter into the area. So anytime the system status is changed, it's a while loop built into the system, and each of those while loops designates a separate state for the system. And the last major section over here is once the system, if no other option has been chosen, the system will default to the arm status. Before doing that, however, it will check to see if all doors are closed. It's no good securing a room if one of the doors is left open and won't trigger the alarm system. If that is correct, then it will initiate the grace period countdown. As I mentioned, it will allow you to exit the area without setting off the alarm. After the timer has elapsed, the system status goes into armed, and it will continually check for input from the door contact sensors. If a door contact sensor is triggered, it will check to see if it is the specific door chosen earlier. If no, it immediately triggers the alarm and goes into the alarm status, where it waits to be disarmed by the pin pad. If the delayed entry door was chosen, it will momentarily trigger the buzzer. It will also trigger the entry timer. This will give you 15 to 20 seconds to disarm the system to make sure you're not deafened by the alarm. Over here, the grace period entry countdown has started. It checks to see if the timer has expired. If it has not, it will check to see if the correct pin number is entered. If it is, it will disable the timer. If the timer has expired, we're back to the alarm status, and that will come with all the bells and whistles that it sounds like it should. And again, we're back to waiting for the alarm pin code to be entered, where it will silence the alarm and return the entire system back to disarm status, and we're back to square one. Skip past the smaller workings of it, just so I don't run out of time here. So for my testing analysis, I did two tests. One was the wireless signal strength test, and the other one was the magnetic positioning test. As you can see over here, what I did was I laid it on a measuring sheet and tested the various distances and positions that the magnet would allow for triggering of the reed switch inside the door contact sensor. This one actually turned out a little bit different than I was expecting. I was expecting a lot more utility with that magnet. So in a second build of this particular project, I would go with a much stronger magnet. So the results of this test are actually look like this. So the way the test was performed, as you can see on the previous screen, was the magnet was originally lined up center to center with the reed switch internally, and then after the distances, the trigger distances was figured out, it would be offset by 2 millimeters in each direction in successive tests, to then move it away to give me a rough idea of what the trigger areas were. And this was the result. This was not at all what I was expecting. The center of the magnet doesn't trigger the door contact sensor at all. They can't be lined up correctly. They have to be offset by about 14 millimeters before any triggering of the reed switch is encountered. And it's not pole specific either. A lot of reed switches very specifically react to south pole, but this here was completely bipolar, and reacted more or less similar on both poles of the magnet. However, it was almost completely separate from it and still triggering it, but not across the center. If I had more time, I would have liked to have experimented a little bit with some iron filings and gotten a better view of the magnetic field surrounding this. However, at midnight, there are no stores open selling iron filings to test this particular feature with. And I don't want to run long, so the testing and analysis for the wireless signal strength also didn't go according to plan. Due to the nature of the XB testing software, the XCTU, they require both jumpers. They require a jumper to be shorted on both modules. However, once it was inside my project, I couldn't short that jumper, and I was missing about half the data once I went to do the analysis of the test. I collected about 3 pages worth of tests. I had no signal strength, transmission signal strength to compare it to. So I know what it receives at, I have no idea what it transmits at. So I would have to do a better design on this particular test were I to attempt this project again. So conclusions. Really the overarching theme for my project was more planning would have resulted in a whole lot less lost time. I had to do 3 iterations of my project in the main code, and they look very different from each other each and every time. Probably the biggest benefit is learning to think like a programmer. Rather than thinking if X then Y, sometimes it's if not X will get you a better result or a cleaner looking code than what you're after. So at the end of the day of my project, I learned a lot, mostly about programming, and this really should be up on my wall as a mantra. The amount of times something was plugged in wrong or simply a 1 was missing where it should have been there really lost me a lot of code. Yeah, it really lost me a lot of time. So that is my rough takeaways from the project. So I'd like to do a quick demonstration of it. Oop, I've knocked it out of the way. Fantastic. Can everybody see that back there? So, by default, the password on this is 9876. So I'm going to turn the door chimes back on. 9876. There we go. As you can see, the LCD screen changes. Blue is the various modes, green is disarmed, and red is fairly self-explanatory. So now that the chimes are on, anytime the door is opened or closed, it sends a signal and an alert is given. B will allow me to change the grace period for entering and exiting the area. So 9, 8, 7, 6. We're going to put in 15 seconds. Any time exceeding 120 seconds is overwritten with 120 seconds. Having 999 seconds to exit a room seems like a little bit of a security flaw. Yeah. So D allows me to change the entry door, basically picking which door I can leave without enter and leave the room without setting off the alarm. So right now it's set to the front sensor, but I have a handy door over there, so I'm going to change it to that door. And finally, changing the master pin code. This one took me the longest, and system flags was what actually solved it. So let's go with 1, 2, 3, 4. In front of the thing, 1, 2, 3, 4. Pin is actually remembered between power cycles. If I completely unplug this from the backup battery as well as the wall, it's actually written to the EEPROM, which will allow me to remember it between boots. So now we're going to arm the system. So I'll use 9, 8, 7, 6. Surprised it doesn't work anymore. 1, 2, 3, 4. Oop, it's still in that mode. There we go. There we go. Being a little cantankerous today. So I have 15 seconds to leave the room without triggering the alarm. And now that the alarm is set, if I enter through this sensor, it will immediately trigger the alarm. Whereas if I enter through this one, I have a limited amount of time. There we go. To get over here, apparently I wasn't fast enough. And disable the alarm. Oh, the door's bouncing. So that is the demonstration for my wireless alarm system.
All right. Good demonstration. Can you bring up your schematic for your door sensor unit?
Schematic for the door sensor, yeah.
Yeah, so, you mentioned that, let me just get my bearings here. You mentioned that, you had issues of, battery life,
I did.
so could you comment on how you would do things differently perhaps in the future to alleviate that? And perhaps indicate what is your battery life at the moment?
The battery life is absolutely abysmal on these. They last for about 2 hours. They also do not put out a sufficient amount of current to run longer than that. Is 2025s output about 14 milliamps each. The 2032s put about 19 milliamps apiece. The XB module draws 25 milliamps. So I did not, when I was planning these, I did not spend enough time on the battery design. So next time I would probably go with a Sierra, I believe it's 123A, which is like a short AA battery in the 3-volt range, which being a lithium battery should give me.
But will that solve your current consumption? All you're doing there is patching the fact that your device still draws a lot of current.
Yes, and that actually is another thing that I'd like to look into, because I suspect it has to do with the way the XB unit is programmed internally with pull-up and pull-down resistors. I should have.
Oh, I don't. What's your quiescent current when it's not transmitting?
When it's not transmitting, is 26 milliamps.
So you're never going to get battery life out of this. If it's just sitting there chewing 26 milliamps, you're never going to get battery life out of this. Right? What is it doing when it's sitting there doing nothing?
Sitting there doing absolutely
It
nothing.
must be doing something for 26 milliamps.
Well, it's not. I guess it's not doing absolutely nothing. It's communicating with the master module.
Why?
Because it's not in sleep mode.
Well, besides not being in sleep mode, why does it need to communicate with the master module all the time?
Because of the manner I chose to update the pins on this, it's a combination of check every 500 milliseconds and pin interrupts.
So, okay, so, again, a pin interrupt, what does that entail?
Anytime the XP module detects a state change on the connected pin, it will transmit that pin change to the master module. Earlier on, I had intended on programming the door was left open feature, and unfortunately that was leaving that aspect of the programming in there was an artifact of that, and unfortunately it cost me my battery.
Well, I think it's the other way around. If all you had done was use interrupts, you would be saving a lot of battery, because I still don't see why this thing has to be transmitting all the time. It really only needs to transmit when there's an occurrence.
Yeah, and that requires a more in-depth reading of the data sheet on this thing. This is about a 300-page data sheet, and there is so much to it. I have barely scratched the surface other than the line passing aspect of it.
Okay.
So I know I could get more efficiency out of these modules.
Well, it's not efficiency, it's just, if you're sitting there just bouncing away all the time, you're just wasting battery, period. You're never gonna, using that approach is never gonna solve anything. If it needed that to make sure that maybe, I don't know, make sure that nobody stole your door, or whatever, I would, then it would be a scenario, but even there, you'd be much better off putting the thing to sleep every second or two or whatever, and waking it up and test, right? You gotta ask yourself again, how quick does it have to be, how often and how long does it have to be awake to actually do its job?
Yeah, and that's definitely something I've considered for a second iteration of this project. Unfortunately, I spent most of my time on programming, and
Well, that is a programming thing.
oh yeah, for the main code rather. I spent most of my time programming the main code, and as I mentioned earlier, if I had been a little more efficient with my time, I would have had time to look into aspects of that. I knew it was a problem. I've documented it in my logbook. Unfortunately, Symposium is now, and it's not 2 weeks from now, so I didn't have time to address it.
What's the purpose of C5?
C5 is just the decoupling capacitor.
Decoupling of what?
Well, for there, it's to ensure that VCC and ground aren't shorted together.
That'll solve nothing.
Well, it's
How does the capacitor prevent VCC and ground from being shorted to each other?
well, you can't pass DC. You can't pass DC.
Take C5 out of there, you can't pass anything through an open unit.
If you open it. No, that acts as a small. Well, the decoupling capacitor is essentially a small reserve to smooth out ripples in voltage coming from the batteries.
Battery has ripples?
No, I got very much into the habit of putting decoupling capacitors everywhere, and clearly I did not think that one through as...
No, but there is a reason for having a C5 there, but it's never, you could have a power supply on the other end, you can have whatever you want. C5 has nothing to do with what's happening on the other end. It has everything to do with what's local. When is C5, let's say it is a decoupling capacitor, which it is, when is it most effective?
Whenever switch 1 is pulled low.
No, that's probably at least your worries, actually. When is C5 most, where should it be to be most effective, I guess?
As close to VCC as
Why?
possible, in order to essentially act as a tank for to maintain stable voltage.
Because of what?
Changes in, or drops in voltage,
Caused by what?
power consumption in the circuit.
No, power consumption happens.
Well, say for example, whenever switch 1 closes, that's going to cause a short to ground.
No, it's
Well, not
not.
short. It's going to provide a path to ground for the system, and that will maintain C5 here will maintain 3 volts in this case, ensuring that
Why?
E3 still stays operating.
There's other, you're right, it's due to transitions, the reed switch, the last of your worries. There's other things that are transitioning here. What other components here have transitions? I know a lot of them very quickly, all the time, in your case, because of the way you programmed it.
My pin change reads? I'm not quite sure what you're getting at, sorry.
What is inside U3?
The internal circuitry, all the transistors for the,
Yeah, they make up what?
like,
Let's Zigbee chip, what's inside of it? Their basic concept.
all the transistors.
No, as a block diagram. What's inside the Zigbee chip? If you had to hazard a guess.
I'm not quite sure.
If
where
you
you're
had,
going.
if I came in today and said, you're gonna design a Zigbee chip, draw me a block diagram, what components, what blocks are you gonna draw?
The communication module,
What else?
the pin registers for
Registers, okay. So A to D, D to A possibly. What else?
Yeah, it has both A to D.
What else? The whole thing's gonna work by itself? What's gonna control all that process?
The microcontroller.
There's a microcontroller in there
Mhm.
that has all those transistors that are switching very quick all the time, millions of them. They create transients. That battery, how far is it from your Zigbee, from the microcontroller, from all that? How far is it?
The first one is about 3 inches. If you go
3
by,
inches.
by trace, that's a fairly,
So what's the impedance of that line?
I haven't measured it.
No, but you could have calculated it based on your trace width, dielectric, that, and there is an impedance, right?
Oh, yeah, absolutely.
So that means that when all those transients are happening, and your microcontroller is trying, or your Zigbee is trying to work at 3 volts,
Mhm.
and it's drawing from those batteries, and there's an impedance, what does an impedance do? What does it limit?
And it limits the amount of current.
Current, so if the current is limited, what happens to the voltages?
The voltage is going to drop
So why do we put C5 in there?
to maintain voltage whenever there's,
Well,
in this case,
to
trade.
give a little bit more current, give that charge of current into your micro, or the Zigbee component,
Yep.
right? To make up for the fact that it's not an unlimited hose of electrons.
No, absolutely not.
It's got a limited amount coming in at a certain rate. Therefore, if C5 is not there, it's not gonna make up for the difference in it.
Yeah.
Okay, and then things like voltage drops, things like that, so what's that, why is that an issue?
Well, if the voltage drops too low on your VCC pin, you're going to go into brownout, or you're going to completely disconnect the.
Exactly. Or you can get transients going elsewhere that you don't want them to go, okay? So C5 is a decoupling capacitor, but it has nothing to do with if it's batteries or power supplies or, the only thing it sees out there is one single line with an impedance, that's all it sees. Okay? Yeah. That just blew wrong. Anybody else? No. We're out of time. All right, thank you. coming back. So we're gonna have I didn't explain that at the start, but we're gonna have about a 10 to 15 minute interval between presentations, just to do our setups and change our presenters and such. For those of you in the audience here, we'd also ask you that if you have to exit and come back, that you not come in when there is already a presentation in motion, please. Okay, so next we're going to look at Sydney Moore's metal detector. So he's worked really hard on this project. He's been able to not annoy anybody in the lab with the tones as we've had historically in the past. So good job just in doing that. All right, so there he goes.
Alright, so my name is Sydney Moores, and I'm an industrial student in the Electronics Engineering Technology course, and my project I'll be going over is on a metal detector. So the goal of this project, was to produce a sound or a tone when the metal detector is placed over top of a metal object. So this would detect objects varying in size and material, and the goal was to make it an affordable product. So I did want to give a budget, so I plan to make it around $100 for the price. I wanted it to be portable, being able to take it around with you, and I wanted to be able to change the audio device that you're connecting to if you wanted headphones or your own device to connect to it. So for powering the circuit runs off of 18 volts DC, and this 18 volts comes from two 9-volt batteries. In the circuit, there's an on and off switch, but it's connected to a light, and the reason for that, my decision to add a light was so that if sometimes you could leave it on and you forget it on, so because sometimes when you're not detecting anything, it won't make any sound. So and also to show when the battery is low, so when you know that you'll need to change the battery to. So I just wanted to go over the main functions of my project. So the project uses a coil, a hand-wound coil that's 21 turns, and it's 4.5 inches in diameter. And this is what you're holding over top of the metal. So, and the input oscillator in my circuit, it takes this the inductance from the coil when held over metal, and it outputs this as a frequency that varies based on what you're detecting. Now, there is also the frequency adjust, which is a variable potentiometer, or a variable capacitor used to vary the frequency of the input oscillator. Now this is only meant for initial adjustments and calibration. Once you have it set to the proper frequency, you won't need to adjust it later on. So both of these frequencies, both the input oscillating frequency and the reference oscillator frequency, they both are fed into a mixer. Now this frequency mixer takes the difference of the two frequencies and it outputs that difference. So when the input oscillator varies, say it decreases its frequency, the difference between the two frequencies, the input and the reference, would become greater, and the output of the mixer would also increase based on that. Now, this frequency is then fed through an audio amplifier, which amplifies it louder so it can be heard at the proper audio level, which is then controlled by a 5K potentiometer, which varies the volume that you want, which is then outputted to whatever device that you're using, say headphones or earpiece. So I just wanted to show my PCB, just to go over the layout and why I chose to put things where they were. So first of all, I'm going to go over why here the coil input, this is the jack connector, it's a TRS, tip ring sleeve connector for the coil input, and there's also another one on the right side for the earphone input. Now, the reason why they're so far apart is because the coil input on the device needs to be on the front side of it, where it'll run down the shaft of the device, so the coil will be at the ground, and the earphone output is facing towards the person so that it can run on the side closest. And up at the top, these connections up here, these are for the connections that would go to the top of the front control panel of my enclosure. Now these are connected to the switch. The switch is the first one up here. So that would lead to the switch connecting to the battery, and this pin here was for the ground connection. And these three here connect to the 5K potentiometer for varying the volume, and the last one here is for the light on the front. Now the reason why they're all on this side of the board is so when it's facing inside the enclosure, they all go around the same side when you're running the wires, so that way the enclosure can open up to the right side and there's no obstruction. And at the bottom down here is the variable capacitor. So the reason why it's on that side is when you open it to the right, you'll be easily accessing the variable capacitor on the left side. So there was a lot of time put into designing this. I made it so there's no jumper connections. All the traces, they I put them in such a way so they all run underneath the components like the resistors and you can see up here, this is the transistor here, and there's that one's for that one's for the reference oscillator, and this is the second one. This is for the input. See, it connects to the coil input, and the one up here is for the amplifier, and the one down here is for the mixer. So these are all the same type of transistor. They're all the 2N3904 transistors, and they're all the same because they're common transistors, and they're all the same. So I just wanted to go over my parts of my schematics. So for the input oscillating frequency circuit, so as previously mentioned, it's 21 turn coil, 4.5 inches in diameter. This is connected into the jack shown here, which is the actual coil itself is around 100 microhenries. This paired with the capacitors C2, C3, and C4, they produce the resonant frequency using the transistor shown here. So this changes based on what metals you're detecting. So the inductance will actually change based on what you have underneath the coil, and the reference oscillator circuit, it uses an inductor rated to 100 microhenries. It doesn't change. This one's supposed to stay constant, and as shown, there is the C10, which varies the capacitance. This goes between 18 and 300 picofarads. And just like the previous one, the L2, the inductor, and C10, C12, C13, C14, they produce this resonant frequency using the transistor Q3. Alright, so this shows the frequency mixer, and it also shows the audio amplifier circuit. So this takes as shown here, it takes in the output, the emitter of Q1, which was the input frequency, and down here is where the emitter of the reference oscillator runs into. So in the mixer, the emitter of the reference leads into the base of the mixer Q4, and the Q1, the input frequency leads into the emitter of Q4. So this is where the actual the difference of the two frequencies is generated, and This then leads into the transistor Q2, which then amplifies the circuit based on the values of R5 and R4, which is then outputted into the earphone, which is controlled by the 5K potentiometer for varying the volume. Alright, so just to show what the actual enclosure and the top panel controls look like, and the actual body of the actual project. So on the left-hand side, you can see on the top of the actual enclosure, the light is on the left side for the enclosure, and the switch and the volume are also there. And on the interior, they run along the interior of the enclosure. And on the bottom, there is the stereo connector. So that's your audio output device. So that would be facing towards the person. And the back side, it doesn't show on there, but on the back side of this, that's where the coil connects to the actual the other side of the actual enclosure, and it's shown here in the actual full structure. So as you can see in the bottom, there is the sensor coil, and this runs using a shielded cable. It's wound up the actual the shaft of the device, which then leads into the enclosure. And as you can see, there's also a piece of the pipe that also runs up on the top. Now this is for the actual handle, and the reason for it being above it like that is for balancing, because having it further in the back would offset it, and there would be more weight in the front of it than there would be on the back, so it would be more heavy. So that's why the handle goes up at the top. Okay, so I just wanted to show a little bit of the calculation I did for it. So there's two calculations I had to do. The main ones were the frequency and calculating the gain. So the frequency, the actual coil I wound, I measured it with a LCR testing device, and the actual inductance of the coil was 126 microhenries, so it was a little more than what I anticipated. So to counteract that, instead of making a whole new coil or trying to adjust it, instead I changed the values of the capacitors. The C2 specifically, I changed because that changed the actual frequency of the input oscillator. So and also I show that I calculated the gain of the amplifier. So it needed to be loud enough to be able to be heard. So I chose a value of 154, and I chose the components, the 1 megohm resistor and the 2.2 kilo ohm resistor to get that value. So I did a few tests, on the device. So the first test I wanted to see is if the actual reference frequency was consistent, if it had any variances or if it changed at all. I did the test based on, like, I wanted to see if putting it towards the metal, if that would affect it at all, and it didn't. I found out though that the frequency does vary a slight amount on the reference. This varies around 20 kilohertz, or 20 hertz. So it wasn't a huge amount, so it didn't seem to be a problem. I also wanted to see what the actual range of the device was. So what I was doing was I'd put the actual coil up to the metal and I'd gradually move it up every centimeter, and I'd record the values of the frequency. And what I found is that the frequency seems to it seems to have an effect on it for around 10 centimeters on the vertical. So you can hold it around 10 centimeters above the metal, and the horizontal is around 8. And I noticed that it's a lot more sensitive on the actual vertical than the horizontal. So that was what the general the project, and so I will now do a demonstration of the actual project. So I'll just be using a stereo device just so you can hear it. This isn't actually required when you're using it. You normally use an earpiece. So for this test, I'll just be using a piece of metal. It's a pipe adapter. It's made of steel. So there is a little bit of white noise, and that's just due to the stray capacitance of the actual coil itself. So as I move it closer to the object, you will hear the change in sound. I don't know if this is loud. It's kind of as loud as it gets. So. But you can hear, as I move it over the object, you can hear the change in the frequency, and gradually it changes. So you can see it's not that far from the object. It kind of has to be fairly close, but I mean, for a prototype, it does around 10 centimeters. So yeah, thanks for listening to my presentation. Yeah.
All right, thank you. questions?
Yeah. I have, like, the first question, actually, thanks for the presentation, it was a good presentation, and good job too. What determined the frequency of the main oscillator? Why did you choose like 400 something?
Well, the reason why I chose that value was because I needed it to be high enough that when I filtered out noise, it wouldn't filter out the actual frequency I was looking for. And also, it's a lot more reasonable to use those values because then the components aren't either too big or too small. So that was kind of the in-between.
What was your frequency again?
It was around 450.
In your
Kilohertz.
searching, you didn't see that particular number pop up anywhere else either?
Like, what do you mean?
Like the number 455, that's never,
It's, it might have popped up.
it definitely did.
Should have.
I know what you mean.
Yeah.
That's IF, yeah. Okay, and about the mixer, I thought that when you use a mixer, you generate like the sum difference and of the frequencies involved and harmonics. So I thought that you may need like a filter after the mixer just to keep the
Yes,
frequency you need, but I didn't see it here, so I don't know.
It did have
Makes sense
a low pass filter after the output. I don't know if I need to show it or.
Yeah, bring your slide
Yeah,
up, please.
So on the actual the mixer, so there is a filter. The filter doesn't really happen till after the amplification. Mainly it's for this part here with C6 and the resistance here. Also something I was going to mention, I forgot to include it, was that the actual device itself you're connecting to is supposed to have a 20 mega ohm resistance on it. And the reason for that is to filter the noise. And for most cases, they don't actually have that resistance on them, right? So I made an adapter, a little short adapter to it, which has a resistor across the tip and the ring and sleeve of the actual cable.
Okay, yeah, you should mention that either on the block diagram, like to show that you have like a sort of filtering just to keep the difference. The
Yeah.
difference. Okay.
In the document, the drawing package, it was included, but I could have shown it in the slides too.
Your Q4 does the mixing, which you stated was the sum and difference, which is very good. How does it, so it's really the creation of new frequency components, right?
Yeah.
Okay, so how does it do that? What's the mechanism that causes that to happen?
The mechanism that causes it is the actual the reference frequency controls the base of the actual switching of the
It's not switching.
the
If you ignore Q1 input there for a second there, the input at the emitter there, okay, what kind of circuit is that?
it's a like I'm not sure.
Just ignore, you see where it says Q1 there? You've got R8, and it goes into your emitter on your Q4 there. Just ignore that for a second there.
Okay.
If you look at the rest of Q4 and its surrounding resistors, okay? What kind of circuit is that you saw in first year?
You mean,
It's an amplifier circuit, right?
yeah, I was,
So what kind? Common,
common collector, or common, yeah, common collector. Where's it?
common collector. What else? What about the biasing? What type of biasing?
It's, forward,
No, the resistors are laid out how for biasing? There's self-bias, there's one that you guys learn all about. It has to do with two resistors and a voltage source.
We've got R11 and R16.
Yeah, what do our 11
Keep
R16
understanding.
form?
Trying to think, I can't think of the name.
Voltage,
Voltage divider.
there you go. So it's actually it's not a common collector, it's a common emitter voltage divider bias, okay, amplifier, right? So that means it should only amplify Q3, the signal coming in from Q3.
Right.
But it does more than that, because it does the sum and the differences of Q3 and Q1. So again, my original question was, what mechanism is required for, instead of just being a regular amplifier, it being a mixer, is it, when we want an amplifier, we want what type of, we want an amplifier to be linear, right? Because all those amplifiers you guys looked at were linear amplifiers. In other words, the gain was always
Well,
constant.
constant.
You calculated another one there a while ago, and you said the gain is this much, right? Okay, so what sets that gain
What sets the gain?
in general?
It's mainly based on the resistance on the base and the collector.
It's AC gain we're talking about here.
Um,
Go to your calculations for a second.
yeah.
I know it's not the same circuit. AV, right?
Yeah.
See AV there? It's based on what? What factors control AV?
The collector, the resistance on the
Okay.
collector,
And what else?
and the emitter,
And what else?
and the forget what that.
Little RE. Let's call it little RE.
Little
Okay. Alright? So obviously RC and RE are fixed.
Mhm.
So little RE, if it was made to be variable, what would happen to your gain?
The gain would vary as well.
It would vary. So let's go look at RE, little RE. What makes little RE change?
The little RE varies based on the current on the base.
Well, look carefully. It's a current on the base, but really it's,
It's the
go the other, next one, right? If it's a base, go one more, go to IB. How did you calculate IB?
it was based on the base, the resistance across the base plus the beta plus 1 multiplied by the resistance on the emitter.
That's right, okay? That is in other words, that's the emitter current, right? Which will be a much bigger effect than IB itself, right?
Right.
So let's go back to your first circuit there. if your emitter current is changed, where's your emitter current flowing?
It's flowing down here.
If it changes, in those other formulas, that means your gain would change, right?
Right.
So how do we make the current change?
By varying the voltage,
Not the voltage,
the resistance.
no, resistance is fixed. What's coming in from Q1?
What's coming through Q1 is the frequency,
No,
the-
frequency,
the-
frequency is a rate of change or something, it doesn't come in or do.
the current.
That's a current. A current going in and pushing back out, right?
Right.
Because it is changing back and forth, back. If it's coming in and out on that node, what's happening to IE in that node?
It's also
Changing.
changing
At the same frequency as
as the
Q1?
Q1.
That means the gain of Q4 is changing at a rate of?
One.
Of whatever frequency is coming in there.
Yeah.
It's making that a non-linear amplifier.
Okay.
Right? That's a common trick that's used in a lot of telecom stuff. It's a common trick. We're injecting in there to change the gain, making this non-linear. That's where you're getting your mixing.
Okay.
Because otherwise, all you'd be doing is amplifying Q3. That's nothing. That doesn't give you what you want. You want a difference of, right? Okay. Okay. Good. Anybody else?
What's the smallest amount of metal that you can detonate with your,
I've tested it on quarters, so.
what?
But the smaller it is, the closer you have to be to it.
Okay, what is it in your design that allows you to change that? If you wanted it more accurate, what would it be that you have to change?
It would have to be I'd have to say the value of the actual coil itself and the capacitors as well, because the issue is that the frequency varies based on that inductance value, so you need the inductance to change more, like a greater change. So
Can you bring up the oscillator part of your circuit?
the reference or the actual
The reference.
okay.
That's probably one. So you said that the actual one oscillates at around 450 something.
Yeah, around 400.
What does this one oscillate at?
This one would be around 2 kilohertz more when the device isn't detecting any metal.
So why?
The reason for that is because it's low enough frequency that you won't really necessarily hear it.
I wouldn't hear 2 kilohertz less than 455 is, or 450, whatever is still 400 kilohertz. I wouldn't hear that. You wouldn't hear that.
Yeah, the difference,
The difference.
the difference of the two
Yeah.
frequencies would be 2 kilohertz if the reference was 2 kilohertz greater. So, but when you detect the actual metal itself, that changes the actual input frequency, causing it to decrease. And because it's decreasing, the difference between those two frequencies is greater. And because the mixer outputs the difference, it outputs the greater frequency. And for humans, the hearing range is around 2 to 20 kilohertz.
Yeah, when you're born. You and I probably can't hear more than 15, 16. That's,
Yeah.
do you know what type of topology that oscillator is? Is that something you got into?
You mean a?
Well, I noticed you redesigned the other one there. They're identical oscillators, right? Just
Yeah.
one has an external coil, the other one doesn't. So you had to calculate the new values. you know, oscillators come in different topologies, different configurations. Do you know what the configuration is for these, or what they're based off of, or?
I'm not quite sure what it's called.
Okay. Well, I'll give you two names, you can go look it up, okay? There's a Colpix oscillator, and there's a Hartley oscillator. And this is based off of one of them, so if you get an opportunity, go look up what makes those two up, and then you can answer for yourself what type they are. And that's where those formulas come from, right? Those formulas come from the analysis lab.
Okay.
Because if you're using the other type of oscillator and use those formulas,
It wouldn't work.
No. Right?
Alright.
Where'd you get the formulas?
The actual formulas I got from our Boylsted, I think it
Oh,
was.
yeah, okay, well, then, there you go. You should be able to look there and they'll tell you what kind of oscillator they are. Good.
When you did the demonstration, you had plugged the output, the audio output of your project into the stereo there that you have,
Yeah.
and you mentioned that it was very quiet. How is it normally going to be used?
Normally it's going to be used with either an earpiece or headphones.
Okay.
And that's why it's quieter, because when it outputs to those devices, you know, it's not going to be as loud as projecting it in a room.
So when you did your testing, I guess you were listening with earphones and.
Yeah, I was testing with an earpiece.
Okay, and what was the comparative loudness, I guess? Was it a lot louder than what we heard here?
Yeah, it's a lot louder and a lot clearer than
Okay.
what you could
And what's the reason for that? Like, if you were to look at your schematic, that section of the schematic, what's the reason for that? Because is there not an amplifier in this
Yeah.
area here?
So essentially, you're amplifying it again. You amplified it the first time, and then you put it through that, and it amplifies it again. And during those processes, it would create a little bit of noise.
I'm just wondering why we couldn't hear it a little better, that's all.
Oh,
I think, there's different ways of doing metal detection too, like there's more elaborate circuits.
yeah.
One thing I've noticed with yours is obviously, like you said, there's a 2 kilohertz tone that varies. But I think if you go look at a lot of the commercial ones, it's actually, when there's no real detection, the tone is not really there. So it kind of, as you sweep, the tone gets there and then drops off. So it goes, in your case, it goes from a frequency to a different tone back to a frequency. But when it's at rest, the commercial ones, they actually go to 0. And there's a knob you need, which would be similar to your frequency adjust there to try to get that to 0.
Right.
You know, so, but I don't think your circuitry has that extra.
Yeah, it doesn't have that.
capability. We need more circuitry to do that. Because I can't imagine listening to
No.
2 kilohertz tone for the whole afternoon.
True.
Go nuts.
Is there a volume control on?
Yeah,
on
there's
that?
a volume knob on
Okay.
the top of it. So when I was demonstrating it, I had to turn that one up to max and then turn that up as well.
What, your volume knob, you said it was a 5K
Pot.
pot?
Yeah.
Well, linear or log?
Linear.
Why?
Because you need it consistent, right?
Well, it's controlling what? What's it controlling? It's controlling the audio volume?
The audio volume.
So I think most people in the know here would tell you it actually has to be log. Did you wonder? You think?
Yeah, that's a good question.
Could you answer why? Have you encountered somewhere maybe where we did talk about log? You know, why are there log pots versus linear pots?
I don't recall ever.
Was it originally intended to be linear, or you just happened to buy the pot and it was a linear pot?
I looked for a linear one because I thought that's what it. could have been?
Well, I'll tell you, it should have been log,
Okay.
but I'll let you discover why. Most audio control pots, if they control audio directly, are log pots.
Okay.
Okay? Again, I'll let you.
Would that have made it louder?
Loud is a relative term, but it would have affected your perception of loudness.
Okay.
Yes. Do you find it's loud
When it's the highest.
the highs and you have very little control over the loudness? When you go down, it gets really,
Yeah.
yeah, and then there's very little control. The log pot will solve your problem.
Oh, okay.
All right, in case we're out of time?
Yeah.
Very good. welcome back. Just before we go to Brandon Ryan and his EKG machine, I just want to remind the audience that there are instant feedback forms all over the place, and we encourage you to fill them out and to bring them up to the presenter once he's done. It gives him a good idea of how the audience feels. And be honest, you know, there's what he did positive and what he did negative, and you know, it's good that they get both good and the bad. Just be fair, right? And so anyways, please fill those out and put their name on top. When we get an opportunity, just drop them off to them. All right, so Brandon, good to go?
Yep, and one moment here, just have to.
So Brandon's gonna present his project, which is a electrocardiogram machine.
Hi there, I'm Brandon, and this is a reattempt of a EKG machine from last year's SPL project. This year's project has been far more successful than last year's. I don't know if anyone remembers my last year. I think a couple people remember it. It didn't work out so well. There wasn't any base functionality at the end. Enclosures weren't done. This time around, things have changed a bit, and I would like to walk you through it here. So today, I'll just be going over what the idea was behind the project, also explain a little bit on how ECGs work, because it's important to gain an understanding of what my project is essentially, and what it's applicable towards. I'll also be going over some of the project documents, and describing the project in a little more detail for the technical audience, and a demonstration of functionality towards the end. Right, so in basic terms, an EKG or an ECG, the terms are kind of interchangeable, is an echocardiogram. There's a bit of a mix-up between the terms ECG when it comes to the output waveform and the actual device itself. So for the sake of this presentation, whenever I'm referring to the device, I'll be referring to the ECG. Whenever I'm referring to the waveform, I will mention the ECG waveform. Essentially what it does is it measures the electrical activity within the heart. So as your heart's beating through its normal cycles, what's triggering it to beat is an electrical impulse sent from the brain. And that impulse can be measured if you have the right tools and you have the right setup, which I'll be going over in just a bit. And typically, the output of this is put onto a graph for doctors to analyze and make assumptions on. So some people might be familiar with this form of an ECG, which contains paper graphs. And as we can see here, I believe it's the mouse showing up. What's that here? See that? Okay, cool. So this one is an example of a 12-lead ECG. Each one of these is measuring a certain aspect of the heart from a different angle, and then the device compiles this information onto a paper graph. But I think the form of EKG that most people are familiar with is this one, which you've probably seen before. You've probably been strapped up to one before, where in a hospital it's a little more of a precise instrument, and it's primarily digital, being able to send files throughout networks, that kind of thing. So my device doesn't work in the same way as a typical hospital device. Hospitals have the luxury of having far more advanced equipment, and thus are able to attain higher levels of precision with their equipment. This device, for the sake of trying to minimize cost and make the assembly process easier, I've opted for a bipolar configuration. And so what that entails, which I believe I can show here, let me just skip ahead. The bipolar configuration only relies on these 3 electrodes here to measure the heart. Whereas in a hospital, you typically have 6 or 12. You have a lot more electrodes than what's found in this one here. Something important to note, the term lead is separate from the term electrode. So if we skip back to the image here, the electrodes are the actual tabs placed onto your skin, but the leads are the measurements essentially taken between these 2 points. So a measurement from the right arm electrode to the left arm is 1 lead. Another one down here, left arm to left leg, is another lead, and so on. Yeah, so this presentation is pretty limited in how technical I can get with the measurement process. There is clearly a lot to dive into here, a lot of dense medical literature. However, it's not just the sake of it going over your guys' heads, it's the sake of it going over mine. So I don't feel fit to describe too much of it in detail here. So the virtue, or I guess the theory behind the bipolar configuration is that it creates something called an Einthoven's triangle. And so what this is, as I mentioned before, with the leads defining the measurements measurements between 2 points, each one of these leads essentially measures the electrical impulses from a different angle of the heart. If you were just to stick a bunch of electrodes on top of the heart and measure it, you'd only be measuring the top muscular region and the electrical impulses on that. By having a triangle, you're able to get a fuller picture of the heart without sacrificing, without losing any sort of clarity or anything like that. So here, so one of the main uses of an ECG is to determine issues, essentially, in the body. Not just issues relating to the cardiovascular system, but all sorts of issues. So, actually, let me skip ahead here and show this first, because I feel like this is probably a little easier. I think most people are familiar with these sorts of images here, with how the ECG waveform looks, right? So that can be broken up into a system of components. So this big spike here is called the QRS complex. This flat region here, that's typically flat, and it's not in mine, which we'll get to in a second, is the ST junction. Then you also have the T wave and P waves here. And from those, depending on what behavior is present, you are able to make assumptions about a patient's health. So in this case, an alarmed P wave indicates something called atrial enlargement, which is essentially where one of the arteries in the heart is widened for some reason, some biological reason, and that affects the effects of that show up in these sorts of waveforms here. There's also, QRS complex, that big spike that we talked about earlier. One that lasts for too long can indicate hypokalemia, which is a lack of potassium in the body. And it's more than just measuring cardiovascular health. You're able to make determinations on someone's diet, exercise, circulation, all sorts of things. And so, all right, so now I'm going to delve into the actual project itself. I'm going to start with the conceptual drawing. I wish there was a way to show the enclosure as is from here, but I'll have to go without that for now. Essentially, the idea, it's a very bare bones enclosure, no bells and whistles. You have 2 LEDs on the top, one green power indication, just to show that the device is on and functioning. You have a pulse indicator, which triggers each time a pulse is indicated, and we'll get into how that works later in the schematic. Towards the front, you have the input jack, which is where I connect these guys, essentially, because I currently am hooked up to electrodes, and you plug this input, or this cable, into the input here for the device to read. And on the back, it's another 3.5 millimeter jack to connect to a computer or an oscilloscope, whichever one you choose. Delving into the block diagram here, it's fairly easy for everyone to see in the back, right? All right, okay, good. So the block diagram, I believe it's probably easier to start in chunks here. So we'll take this top chunk here, and I'm circling around quite slowly. And this is the power/reference voltage stage. From here, the device is powered by 3 batteries. Yeah, I wish I could show inside the enclosure right now. The device is powered by 3 AAA batteries in series, generating a voltage of 4.5 volts approximately. From that, there's a quick little circuit with just a LED and a resistor in series to indicate power here. Moving on from that, the 4.5 volts is used to create a reference voltage. And the necessity behind the reference voltage is that my project only has one single supply. And so for most op-amp circuits, most op-amps carry a positive supply and a negative supply for sourcing, syncing, configurations, that sort of thing. And except to display a voltage to a computer, the output has to be negative, and that's kind of an issue with when you're trying to hook up to a computer. So instead, I opted to raise the amplified signal by the reference voltage so that the output's able to swing essentially up and down to imitate a negative voltage without actually being a negative voltage, if that makes sense. Coming down here, we have the input stage, which is right here. So attached to my body are the 3 electrodes that we talked about earlier. We have the VN plus, which is on right here, VN negative input voltage here. We have common or ground here that I have labeled. The input is sent through a low-pass filter just to get rid of any excess 60 hertz noise that could be affecting the system, affecting how the input's being read, and potentially masking the signal, because the signals seen by the electrodes on the body are very, very weak, approximately 5 millivolts on the surface of the skin. So any presence of noise is going to completely mask that. It's going to completely swamp that. So it's important that we get rid of that before we start treating the signal and amplifying it. Moving on here to the intermediate stage, this is where the amplification essentially happens. It's essentially an instrumentation amplifier configuration. I don't know how many of you are very familiar with that kind of setup. But if you are, then you might be wondering why I opted to choose 2 op-amps to create an instrumentation amplifier rather than 3. And the idea was that by only utilizing 2, it allows for the device to have other functions, as the pulse LED indicator actually requires one of the op-amps, and another one is used to create the reference voltage. So instead of having to purchase an IC with more op-amps included on the chip, or have 2 separate ICs, I'm able to do all the amplification, all the indication, and reference voltage settings with a single op-amp chip, single quad op-amp chip. And we'll get into the nitty-gritty of the instrumentation amplifier configuration soon here. The manual common mode rejection ratio and gain control. So inside the project are a number of potentiometers which allow balancing of the resistor divider networks that are amplifying the circuit. It's a little easier to explain with the schematic, which I'll show next. However, it's essentially a way to tune out background noise and to get a clearer signal. That's essentially the idea behind it. Moving on here, it's essentially the output and pulse indication stages. So once the signal has been amplified, it's then sent through an output low-pass filter to again filter out more 60 hertz noise. However, before sent through that, it is also used in a comparator circuit, right down here, which once a certain threshold is set with this block here, once a threshold is set and passed by the QRS spike that we talked about earlier, then the red LED will light up indicating that there has been a pulse, which allows, which is just a really nice user-friendly option there. Right, so the schematic. In here, you see the input low-pass filters. This rectangle here that you see, ignoring the, right here, the low-pass filters, ignoring the C5 here, the idea behind this is to, essentially, it's for common mode rejection ratio. So if a signal is common to both pin 2 and pin 3 of the input jack here, it will show up through this potentiometer here. It will be applied to both sides of the resistor network, essentially. And by adjusting the potentiometer, you can balance the network very precisely to the point where any inconsistencies between the two input signals are overcome. Here is the instrumentation amplifier setup I mentioned before. As you can see here, I've included a 470 ohm resistor, R7 here in series with the gain. And I don't have the equation in the presentation. However, I can just describe why I've done that. There's a point in the gain, to calculate gain for this section, essentially, there's a part of the equation that has R6 in the denominator of a fraction. And so the closer R6 gets to 0, you essentially get theoretically, you approach infinite gain, which is just not possible and could potentially damage other components later on in the system. So to prevent that, I've included a 470 ohm resistor to ensure that there is an upper bound to how much gain can be in the system. I haven't gone over the power. The power stage is fairly straightforward. It's just a power switch, the power indication circuit with the resistor here. I opted for both electrolytic and a ceramic bypass capacitor at the input, due to the fact that electrolytics and ceramics have different responses, or different frequency responses, and thus are suited towards bypassing particular types of AC signals. And so I figured that including both wouldn't hurt. And down here is the comparator circuit. It's fairly straightforward. I think we've all done electronic devices right. It's just a simple sort of syncing configuration here where the output signal is measured against the threshold, and if it's passed, then this goes down to the ground. There's not much else to talk about other than there's another output filter here measured at 48.62 hertz, I believe. And that's about it for the schematic. So the PCB. Last year's PCB was awful in many different ways. It was a very rushed design, very sloppy, and I don't think I've included an image here to compare and contrast last year's to this year's. But you're just gonna have to take my word for it, and it was quite bad. This one, however, it's a lot cleaner. It's a lot more sophisticated, in my opinion. It utilizes 0 jumpers when compared to last year's, which included 5, and also includes far wider trace widths and pad widths, whenever possible, essentially, to maximize to overcome any inconsistencies, as this PCB was created using the in-house etching process here at NBCC. So to prevent any sort of breaks and traces that occurred like last year, I opted to play it safe and up the width. Right. One second here, the mouse is fighting me. Yeah. No, it's not letting me. Right. So for here, there's meant to be more of an in-depth demonstration of functionality. However, while I have gotten this to work on my own personal computer at home, currently the device does not seem to want to play well with the oscilloscope software that I have set up here. I don't know if I can screen share this. Do not think so, not at the moment. I can show you, what I can show you, however, is this screenshot here, which was taken on my own personal computer at home, essentially yesterday. I suppose it's going to have to do to try and demonstrate the actual functionality of the project. Currently, it's just I can't show the oscilloscope software at the moment, but it's just a tangle of noise, and there's no order. It's like it's not seeing the input, which I'm not sure what's happening there. However, from this, certain alterations can be made. So I think I talked about earlier how a depression in the ST junction can indicate myocardial ischemia, which is essentially a difficulty in circulation in the extremities, especially the toes and feet. And that's something I actually have. I have very poor circulation in my feet, and the depression in the ST junction is easily visible here at the moment. We can also point out other landmarks of the typical ECG wave, such as the P wave here, right before the QRS spike, and then the eventual T wave here. Right. So, moving forward, as it stands, despite the current hiccup with the demonstration, the device does work. It's unfortunate that, it's very, very unfortunate, honestly, that it didn't work here. However, moving forward, first step is probably going to be diagnose what's happened here and make sure that doesn't happen again. Second off is going to be properly labeling certain parts of the enclosure. Because at the moment I wasn't able to properly apply any sort of labels to the thing, so it's the power and pulse indicators aren't labeled, the input and output are indistinguishable, and the potentiometers are currently unlabeled. However, I'm thinking of doing that within the week, so it shouldn't be too much of a hassle until then. And, right. There we are. Yep, I believe I'm ready to take questions on.
Does the project function,
Yes,
but you just can't show us that it functions?
yeah, it is.
What was the reason again?
The reason, I'm not sure what the reason is, because I know when I tested it on my Mac was having difficulty, maybe it was an audio driver issue, it was having difficulty detecting that this was an audio input, or measurable at all. The only input it took was from the microphone built into the laptop, and it completely ignored the fact that I plugged it in. When I plug it into my computer, I don't have to worry about that. I have the oscilloscope set up properly right off the bat, and it works. I could could send a video of that. I probably should have sent a video of that in hindsight.
I think you should have prepared in advance that you could have demonstrated today.
No, I had it functioning earlier. That's the weirdest part. That's the weirdest part of all this.
Can you bring up your schematic again?
Yep.
No. Yeah.
Alright.
So, I don't know, is it me or is it blurry?
It's not you.
Okay.
Okay.
Well, it's still pretty small, you know. So in the case of a schematic like that, what we ask is that you also submit a drawing package so that the advising board here can follow through and mark things down and so on. Unfortunately, I didn't even have that.
Hmm?
You didn't submit your drawing package.
I remember I didn't submit it on time. I remember that, but I did submit it afterwards,
Well,
as soon as you pointed it out.
It's got to get printed and so on, right? So I mean, if you don't submit it on time, it doesn't get included,
Oh, okay.
right?
Gotcha.
All right, so I might as well have to make do with this, I guess. You mentioned that C2 and C3 are bypass capacitors.
C1 and C2.
Or is it C1 and C2? Okay,
Yeah.
sorry. And you said they have different characteristics,
Mhm.
and because of that, in AC, therefore you selected them.
Yeah.
So what are their different characteristics?
Don't remember it off the top of my head. If I do remember correctly, the ceramic is better for higher frequency AC, and the C1 is better for lower frequency AC. In terms of actual metrics, I don't have that available.
And AC from where?
Any sort of potential transient that might arise from the op amps, any sort of outside signal that might affect it. We are using batteries, so of course there's no expected AC input. However, it's essentially to prevent or mitigate the effects of the unwanted AC signal in the system.
But from where? That's what I'm asking. Are they bypass capacitors, or are they
Mhm.
decoupling capacitors, or are they?
Yeah, they're essentially both. Yeah,
So if they're decoupling capacitors, where should they be?
as close to the IC as possible, I believe.
So why aren't we seeing that in your schematic as a representation of that? Because that's traditionally the way we do that.
It is the way I've done it inside the enclosure here.
And I would expect it to see it near U1A,
Gotcha.
showing that on that.
Okay.
One thing that would have made this easier for us to read too is if you had broken the diagram up into sections, you could have explained a section at a time and caused that section to be enlarged so that we could see it.
Right, yeah.
Can you, just one last question for me. You mentioned the instrumentation amplifier, and you said that you selected R7 as 470 ohms because you did not want the gain to go to infinity. And if it did, it may damage other devices. So, I'll paraphrase it. Okay. So, first of all, I doubt that the gain will go to infinity in a practical device, so what will it go to? And how would that damage the other devices?
So the gain in this system, are you talking without R7 involved, or if
Sure.
with
Yeah, you said you
R7?
put R7 there
Yeah.
to protect other devices, which you
Okay.
didn't mention directly.
With R7 in the circuit, the maximum gain is 4,553.32, and the other devices that I'm worried about aren't necessarily in my circuit. It's if I'm connecting it to a computer I don't know enough about audio cards and how they function to know how they would respond to a 20 volt or 30 volt input signal.
You're gonna get 30 volts out of this?
I've gotten 20, yeah.
You've gotten 20 out of a, what, 4.5 volt supply, you've gotten 20 volts.
It's been an output, yeah, at the output.
No, you have a 4.5 volt supply,
Mhm.
and you're able to get 20 volts out of the output. Buddy, let's look at that thing, ball it and sell it, because we're gonna make money.
I think you were using the scope incorrectly if you
Yeah.
saw 20 volts.
Yeah, I think so too.
What is the maximum that op amp in any configuration could
Top,
put out?
top rail, which should be, yeah, it should be 4.5 volts.
Well,
Or sorry, from the reference voltage, should be 2.25 volts in either direction.
Okay, so again, so my question becomes the 470 ohms.
Mhm.
What are, let's say it's not there. So what is the max gain of that op amp? And at the same time, besides the output circuitry, what else are you protecting?
So without R7, theoretically, right, the gain approaches infinity.
Well, let's talk practically,
ma-
this is a practical.
Practically, the output signal would hit the top rail, and essentially it would be 2.25 volts in either direction at the output.
Okay,
Given the assumption of a 5 millivolt input signal as seen by the electrodes on the surface of the skin. Is anyone really good at math? Can anyone do that right now?
well, it doesn't matter what's coming in,
Mhm.
what's the limit of the output?
The limit on the output is 2.25 volts in either direction. Or
So
4.5
a total
volts, total 4.5, yeah.
So it doesn't matter what's at the input, that's the maximum at the output.
Mhm.
So what is, and I asked you to look this up, and you chose always to somehow dodge that task. I said you have to find out what a sound card expects to see as a line in,
Mhm.
as a voltage. Because yeah, maybe it is too much, maybe it isn't. If it is, and you're damaging things, well, that's the problem with your product. If it isn't,
From what I gathered, my time researching it, it really does depend on the age of the computer, depends on what OS it is, if it's running, if it's a Mac or if it's a Windows. There are
Really?
certain values, yeah, there's certain values that change, especially age, but,
I guess they build them differently now.
I really don't think audio inputs have changed that much.
No, there's a standard there.
Okay.
Whether they choose to follow it or not is their problem,
okay.
but there's a standard there.
Yeah, I wasn't able to get anything conclusive when I looked it up.
Again, I asked you many times to look it up. Okay. So it's all right that you are limiting your gain, but don't say it's because you're trying to save things and you're gonna put out 20 volts and whatever, that's.
Can we come full circle on that now?
Sure.
What is the reason why you should limit the gain then? We're not concerned about damaging things, I think we've debunked that theory. So what's the reason?
I imagine constant output at the top rail might put some sort of undue stress on the op amp itself. Like if it's constantly outputting the maximum that it can.
But is it though?
Well, if R6 approaches 0, right?
No, but if you have a small AC signal coming in, what does that instrument amplifier do at the output?
It amplifies the small input.
Okay,
Yeah.
so it hits the rail, then what?
It's basically just a flat line after that. It's
Forever?
if the gain isn't adjusted, yeah, I see what you mean. So if the gain reaches a maximum, then it's going to keep hitting the rail, but there's still going to be the negative component of that input signal, which is going to dip below the max, right?
It's gonna come back down,
Yeah.
and you'll go back up, and
Mhm.
you'll go back down. But what else happens, and that's the follow-up to Mr. Broad is asking. I'll leave, add a little bit to it.
Yeah, sure.
a open loop
Open loop feedback.
high gain amplifier?
Yeah.
What's the issue?
Feedback, essentially.
Wow, that's actually,
It still has feedback, but that's kind of a vague answer.
what's it gonna do? What is feedback?
What is feedback?
What is feedback?
Okay.
You brought it up.
Yeah.
What's feedback?
Essentially, it's the, some component of the output is applied to the input. So as the device changes,
But
essentially,
in
the output can
in what
transmit to it.
specific relationship though? Because that's actually, geez, I can't even read that. All those amplifiers there, every one of them has feedback.
Mhm. Yeah.
The last one has a feedback with a gain of 1. The middle one has a feedback with a 1 meg resistor. And what you're attempting to do there is also a feedback loop there,
Mhm.
okay, to U1A. So there's feedback.
Mhm.
But when we talk about feedback, oh, it's bad. What do we mean by feedback? What's the relationship there?
I mean, what kind of feedback are we talking about?
No, I'm not sure what kind of feedback you're hinting at.
There's 2 that you should know.
It's not coming to mind at the moment.
It depends on where the feedback is placed, like in reference to the input terminals.
Sydney had amplifiers too, but
Mhm.
his amplifiers were configured differently, so they did what? He had 2 circuits there at the input that were amplifiers,
Mhm.
but they oscillated. Why did they oscillate, and why do yours amplify?
I thought the oscillation had to do with his project in particular and how.
No, but what
And how
makes
that was
yours, what makes your circuit right there
Mhm.
not be an oscillator?
The lack of any sort of inductance or capacitance. It's just a pure.
I can build an oscillator with other devices that'll choose. And you've got a lot of
Feedback
inductance and
resistors.
capacitance there. You've got your board, you got
Yeah.
the leads, you got.
Well, any oscillation that occurs would eventually die out to the resistors, right? That's the idea.
Not true.
I'm not catching what you're trying to hint at, unfortunately.
We gathered that.
Anything else?
I don't know. Can you explain the purpose of R8?
All right, yeah, so the typical equation for gain in the instrumentation amplifier, do you need me to zoom in on that?
Oh, there.
That would help, yeah.
Okay, yeah. So the standard equation works with a resistor of a known value. However, if I want to essentially, if I want to try and adjust that, or sorry, I want to try and have a equal resistance. I don't know where my mouse is. Oh, I need a laser pointer. Okay. If I want to have an equal resistance, oh, Jesus. Okay, I guess we're going with the laser pointer then. So at the output of U1A on both sides with the wire on the top connecting to pin 13 of the IC and the bottom connecting to R9 going to common, R8 serves to balance both sides of that divider network. So by tuning it, you're able to get an equal resistance on both sides, which enhances the clarity of the signal.
What are you tuning? Because you use the word tuning here. What are you tuning?
Tuning. So in this case, we're adjusting the potentiometer to, so we're tuning that essentially.
So are you really tuning something, or?
It's More like adjustment rather than
It's
tuning.
adjusting, right?
Yeah.
Usually tuning, it has to do with frequency.
Oh,
You're
okay.
tuning for a certain frequency or a certain channel. So here you're adjusting, what are you adjusting again?
We're adjusting the potentiometer R8.
No, but what are you adjusting as you set the position of R8?
The common mode rejection ratio. So the idea is that any sort of shared DC signal, I believe, from each side of R8 is, if the resistor network isn't balanced, then it leads to one signal that's present in one input being of a higher amplitude than the other signal. So by balancing it out, you're able to get them equal to each other. That's the idea.
And by signal, you mean, is there multiple signals that emanate off of R8?
No, so it has to do with the connection to common going down and the connection to U1D, or sorry, U1D going up. If there's one signal going in, but it's applied at two different outputs, and if some sort of DC offset is introduced at U1 at the output of U1A, and R8 isn't balanced, then there would be potentially a larger signal going down towards common and R9, and a smaller signal going up towards U1D, towards the output.
And what problem will that cause?
So, God, my mouth is so dry right now. The whole point of the reference voltage is that it acts as it acts essentially like a ground floor or a ground, essentially, even though it's not 0 volts. The idea is that you're using it to reference the values of the output against it. If there's a offset introduced to common, then it's not going to be fully, the relation to the output and common isn't going to be fully accurate, as one signal is going to be present in common that's of a higher amplitude than what's present at the output.
So if you were to take an oscilloscope and measure that signal and adjust R8 all the way to one extreme and the other, what would you notice changes about that signal as measured on an oscilloscope?
It would become, okay, so it depends on which extreme you're going to.
Well, let's talk about both then. Talk about one extreme first and then explain the other.
So as you adjust R8, one extreme would be that the signal approaches what's essentially a flat line as the reference voltage. So the relation between the output and common is diminished to the point where the output voltage, right, output signal is indistinguishable, and essentially it's just they coalesce. I'm missing the technical term here, but in one aspect it's fully diminished, and in the other aspect, the differences between the output and common are greatly exaggerated to the point where it's very difficult to read, very difficult to use.
So what's the difference between adjusting R8 and then adjusting R6 gain? It sounds like you're...
Well, the gain is just about amplitude. So whatever signals, or sorry, R6 is just about amplitude. In one aspect, it's, oh, I see what you're saying. Okay, yeah.
Because it sounded
Yeah.
like to me, you just said that if you adjust R8 to one extreme, you get a signal of 0.
But it's not quite,
Right.
because R8 is affecting the common signal as well, whereas R6 is essentially just an exaggeration of the input signal, or amplification of the input signal. That's what it governs.
Okay.
Quick,
Anything else?
yes.
There's only a minute left, so.
RA is missing a node on the bottom now. And which version of the schematic is this?
This is one that I made in March, I believe.
So it's not your latest schematic?
This, I didn't really add, oh yeah, I didn't get a chance to add the jumper connections into here, so.
That's
GIS
not my issue.
connections.
My issue is R2, R10, R4. You were told to change that layout.
Which one?
R2, R10, R4.
No, wait,
Yep, you know I told you that.
yeah,
And I think you even changed it, so we may not be looking at the latest schematic. So I hope that's not what I'm gonna see in the report either. All right,
Okay, we're out of time.
thank you. All right, thanks everybody for coming back this afternoon to see some more really interesting presentations. Just before we start with Mac here, just a few things to remember. First of all, I'd like to welcome the alternate junior class in here. So what you see here is kind of what's in store for you next year as far as the senior projects are concerned. So watch carefully and by all means absorb what you see. And this is a good situation to learn a few things too. I'd also like to remind everybody that during the question period, it is the panel of advisors, instructors only that are allowed to ask questions, and that's just because of a time constraint. Okay, we are under the quite a tight timeline, and we don't have time to have other people asking questions. Okay, so just for information there. Oh, the washrooms, if you need to use the washrooms, you go out and to the left, they're all down the hall here, so I don't know if you're familiar with this end of the building or not. And also, we're going to ask you, the rear door is unlocked. If you have to enter and leave the room for whatever reasons, please go up that way. It's a lot less disturbing than coming out in and out on the front here. So the back door there should be unlocked, and use that as your egress and ingress, please. So, everybody's good. We're going to start with Mac Anderson from the Industrial Controls Group, and he's going to talk about his Nixie tube clock.
Right on, thank you very much. Well, as you just heard, my name is Mac Anderson, and I'm from the EET Seniors Program in the Industrial Division, and I'm here to show you today my project, the Nixie tube clock. Now, I know not everybody might not know what a Nixie tube is, but you're probably more than familiar with a clock, saying, oh yes, absolutely. I've seen that on my microwave and on my dryer, everywhere. And of course you have, they are everywhere. And you check them just for a moment to get whatever time you need. But why not have a clock that gives you something more? Why have a clock that's only, I'm looking at this for a split second? Why not have a clock that is designed to be looked at? And that's what my project here is today. Now, throughout this project, I'm going to show you what exactly is a Nixie tube and why have I decided to use them. How does the clock work? How is it performed? And then we'll finally conclude on our results of the project from there. So, first of all, what even is a Nixie tube? Well, Nixie tubes are actually just a brand name that is owned by the Boros Corporation. Now, in actuality, Nixie tubes are a numeric gas discharge indicator. Now, they operate by using digits, a stack of numeral-shaped cathodes that are sandwiched between two anodes. And when you apply a significant voltage across the anode and cathode, you can ionize an inert gas inside the glass envelope. More often than not, this is neon, so the digits will ionize and produce an orange glow. Now, that's wonderful, that's just fine and dandy, they're beautiful little tubes, but there's a caveat to this. This is the voltage waveform that I recorded from igniting a Nixie tube. When this happens, as you increase your voltage across your tube, you'll see two distinct events. The point the tube actually begins to emit light and begin ionizing the neon gas, that's known as the firing voltage. And after this event happens, the tubes will then flatline to a near constant voltage known as your sustaining voltage. Now, that's great and all, but I did say this is an oscilloscope capture, so I do have data to go with this. At the bottom there, you can see that was my 0 volt reference line for my capture, and that's perfectly fine, nothing wrong there. This scope capture was taken at 5 milliseconds per division horizontally, so again, nothing out of the ordinary. The problem is the vertical divisions. This was captured at 25 volts per division, which means that my firing voltage to actually use these tubes is at 165 volts DC, and their sustaining voltage is at 130 volts DC. So for me to actually use this clock to get it to work properly, I have to operate and work with safely these voltage levels. So to actually get the clock to work, I'm going to show you the concept drawing of the body of the clock, as well as its system block diagram to show you all the inner workings of what part of the clock is talking to which. Then lastly, we'll go over the flow chart of how the clock thinks and the schematics on how it's physically wired. So beginning with the overview of the body of the clock, on the rear of it, we only have a on-off switch and our 5mm barrel jack input for our 12 volts. The front of the clock is where the current hours, minutes, and seconds are displayed. And also the front of the clock here is made up of a tinted window, just to help and aid in viewability of the clocks, of the digits. I'll touch in on that again later. And then on the right-hand side of the unit, we have our two user interface buttons, being set and select. I'll go into more about how to actually set the time of the clock once we get to the live demonstration. Now, the inner workings of the clock work with this diagram. Up at the top, we start with our mains wall adapter will bring our 120 volts AC down to 12 volts DC before going through our input jack and the terminal blocks to get onto the PCB itself. From there, this 12 volts will go through input protection systems before it is then regulated across two different voltages. Firstly, it'll go through, the 12 volts will then go through a 5 volt linear regulator, which will supply 5 volts to all the logic portion of the circuit. The second path is that the 12 volts will then run through a boost converter, which will then generate the high voltage required. Now, of course, when I said earlier that the tubes require 165 volts DC to fire, that's the minimum. I have to exceed that value for them to ignite consistently. So for my circuit, I've decided to operate at 190 volts DC. The logic portion of the circuit is controlled through my microcontroller, which has a 3 volt replaceable button cell battery feeding it, which allows the clock to retain time after it's been unplugged or moved. The microcontroller's only form of input is from the two previously mentioned user interface buttons. The actual controlling of the clock face is controlled through two shift register lines. The first line of shift registers is responsible for controlling or feeding data from the microcontroller into our driver ICs, which then each control is singular Nixie tube each. Now the second shift register line then feeds BJTs, or bipolar junction transistors, that are then used to either drive the decimal points of the tubes or the smaller dot tubes that are used for the colons of the clock face. Now, later on in the presentation, when I start deep diving into the schematics, due to time constraints, I will not be talking about this second shift register line. So that's the hardware operations of how the clock works. The software operations is a bit simpler. It can be divided into two primary groups. This tree on the left is known as the active process, and this tree on the right is known as the passive process. Now, actively, when the clock is running, this is what it's constantly checking for. It first begins by checking to see if the time has changed. If the time has changed, it will then check to see if it's in a mode where it is supposed to update the time on the clock face. If it is not supposed to update the time, then it won't. If it is supposed to update the time, it will then check to see if it is on battery power. If it's not plugged into the wall, there's no high voltage, so there's no need to update the time anyway. So if it is on battery power, it will choose to not update the time. Otherwise, it will. If the time has not changed, it will then run through a poll of checking either the set and select buttons to see if the user interface has been interacted with. Nominally, when pressing these buttons, they will do nothing. But if you are just if you choose to press and hold, where here it's checking for how long you have pressed the select button, this is where it'll check to see if you have pressed it briefly for less than 1.5 seconds. It will cycle the value of your selected tube, or it'll cycle your selected tube. If you have held it down longer, this is where it'll actually toggle the timekeeping mode. I know this seems obscure for right now. I will re-explain this once you get to the live demonstration, where it'll be much more apparent. The passive process is what runs in the background as the clock is doing all its other checkings in the active process. This is where the actual timekeeping takes place. At the beginning, it'll run a real-time clock, a function of our microcontroller, and it will constantly check to see if 1 second has elapsed. If 1 second has not elapsed, it will perform no action and continue to wait on the real-time clock. If 1 second has elapsed, it will then trigger an interrupt, which will pull the clock out of any other operation it was performing previously. And from here, it'll decide on whether it should increment the time or if it will toggle the colons of the clock face. So this, what it does here, depends on what mode the clock is in. Again, this will be much more apparent once I get to the live demonstration. Now, getting into the nitty-gritty of the hardware of the clock face, or of the clocks itself, the first schematic here is of the microcontroller area. So U1 is the microcontroller itself. This is what I programmed through my inline serial programming header. The set and select buttons are represented here, which are connected to port B. These have internal pull-ups, so I'm checking to see if these pins go low. This voltage divider, made up of R1 and R2, is what is responsible for the clock being able to tell if it is on battery power or not. That is because port A7 here is connected to an internal analog comparator, which is another function of this microcontroller. PA7 is connected to the non-inverting input of this analog comparator. So, with this voltage divider, which is connected to our 5-volt rail from our linear regulator, it is connected to 2 equally sized resistors, which means that this node is approximately 2.5 volts. Now, the inverting lead of the analog comparator has been configured to an internal 1.5 volt reference. So that means that if this is connected to VCC and I do have 5 volts, the output of the analog comparator will be positive. So 2.5 is greater than 1, and I get a 1 on the output. And if I disconnect VCC, PA7 is now pulled low through R2, since R1 would now be floating. So that way I can now checking if 0 is greater than 1.5, which it isn't. So I use the bit that is associated to the output of that analog comparator as my flag to check to see whether the clock is on battery power, yes or no. Using the analog comparator comes at a much greater benefit than running an analog to digital converter and constantly checking the voltage level, because that has an enormous power consumption. So me trying to run this on a button cell battery would not run for very long. Speaking of button cell batteries, B1 here is isolated from the VDD, power input of the microcontroller, through diode D2 and D1. The purpose of those diodes is to isolate VCC from the 3 volts from the button cell battery. When VCC is connected and I have 5 volts coming through D1, D2 is now reverse biased and will not conduct. So this way the battery does not lose charge other than as it would do passively. As soon as you remove VCC, D2 now becomes forward biased and the battery will begin to conduct and continue to supply the microcontroller with power. C1 and C23 are decoupling caps, and C2 is a bulk input capacitor just to help the voltage across U1 not change suddenly when you disconnect power, because I did find through testing that a sudden change in its voltage level would cause it to behave erratically. And lastly, X1 here is my external oscillator that I used for actual timekeeping. The next circuit here is the power management circuits. These are responsible for protecting my input voltage, as well as generating my 5 volts for the logics and the high voltage for the tubes. Coming into the clock from jack J1, it runs through our on-off switch, and then a overcurrent protection diode rated at 2 amps. And then we have a reverse polarity protection diode for reverse input polarity protection. That then supplies it with a clean and protected 12 volts to use. Here is our linear regulator, which then takes our 12 volts and feeds it and regulates it down to 5 volts. And lastly, this is the boost converter for generating the high voltage. Now, I won't be explaining every single component in this circuit, as it is, I think, beyond the scope of this presentation. But L1, D4, C6, and Q1 form the 4 basic components of a boost converter. U2 is my controller IC that I use for switching Q1. And R6 here is the resistor that is responsible for setting the switching frequency of this regulator. And by using switch S4 here, I can choose to either have R6 pulled high to VCC through R7, or pull that node to ground. If that node is pulled high, then that activates a shutdown function of the boost converter, disabling the high voltage part of the circuit. That's under the intentions if you needed to go into the clock for servicing and you wanted to have the logics half of the circuit intact, then you could choose to leave all that running and only turn off the display tubes themselves. Up top here we have R8, R4, and R3. That forms my feedback network for the switching IC. R4 is a 500 ohm potentiometer that I have configured as a rheostat to provide a small amount of adjustment in the high voltage, just to account for component tolerances. The total range of voltage for this system is approximately 150 volts to 220, so you can adjust it, fine-tune it between that range. The next major part of the circuit is the primary drivers for actually controlling the Nixie tubes. And I know this circuit looks very complex here so far, so what I'm going to do is actually focus in on one segment of the circuit, and after I explain it, the rest of it will be much more apparent. So, this portion of the circuit, up top here, we have a 8-bit shift register that is connected to my microcontroller through strobe 1, clock 1, and data 1. Now, the 8 bits of this shift register is connected to 2 Nixie tube driver ICs. Now, each one of these drivers require a 4-bit BCD signal, or binary coded decimal. So this works out quite nicely where I'm able to use one 8-bit shift register to drive 2 drivers. And then lastly, each driver is connected 1-to-1 per Nixie tube. My resistors here, R17 and R18, are my current limiting resistors for the Nixie tubes themselves. These are connected to my 190 volt high voltage bus that runs along at the bottom. And then R11 and R12 here are additional current limiting resistors for the decimal points of the Nixie tubes, as they are much smaller and don't like being highly ionized, is the best way to put it. So that's how I use one shift register to drive 2 Nixie tubes. I take 8 bits, split it up to 2 groups of 4, and feed those 4 bits to 2 drivers. And now I can continue this pattern to drive the rest of the display by doing 3 simple things. If I continue my strobe and clock lines and make those common across additional shift registers, And I use pin 10, the QS prime is the name of that pin for this shift register. I can use that pin as the data outline of this shift register and feed that into the data in of the next shift register. And lastly, I can continue my high voltage bus to feed more Nixie tubes along the bottom. If I make those 3 changes, I can actually chain 3 of this circuit together to drive all 6 display tubes, only using 3 pins of my microcontroller, only using strobe, clock, and data. Now that we've seen how the clock works, let's discuss into, well, how does it perform? Being a clock, first and foremost, there's only 2 things it does. It either keeps time and it shows you the time. Ideally, it does both. The first test that I did was to ascertain the timekeeping accuracy of this clock. So what I did is that I had my Nixie clock running alongside a reference, and I recorded a video at the beginning and end of an interval of time. So for me, I left my clock running for 6 hours alongside my reference. And the purpose of taking a video at the beginning and end is to figure out how far off they start and how far off they end. So by using the video, I could analyze and say exactly, oh, my clock was 300 milliseconds behind the reference. So then 6 hours later, I want to see, hey, is my clock still 300 milliseconds behind, or has it changed? So I use that data to ascertain how much the clock is off of, what's its timekeeping accuracy. Now, the results of this test was done 4 times. First, this was just the primary results as when I was creating the clock and programming it the first time. I only used estimates for my compensation values. We can see that when the clock is awake and it is plugged in, it was running a total of 12.6 seconds behind per day. So every day you left it plugged in, it would be 12 seconds behind. The next day it would be 24 seconds behind, and so on and so forth. When it was asleep, the clock was a whopping over 3 minutes behind every day. So not doing the best. But again, those are estimate values. I use the data here from my testing procedures to figure out how much to compensate the clock. Right now, at the current accuracy of its timekeeping abilities, I can increment it. I can increment what the clock considers to be 24 hours in increments of about 2.6 seconds. So right here you can see, oh, it's awake and it's about 12.6 seconds ahead. Well, I would divide that by 2.6 to figure out how many counts to further adjust how well it's doing. So after calibration, actually wait, before I get onto that, the allotted accuracy, my goal for this clock was to be within plus or minus 10 seconds per day. As you can see by this next test, after calibration, when the clock is plugged in and it's awake, it runs at only 800 milliseconds fast per 24 hours, which is less than a second off per day, which is well within my tolerance I had initially planned for. But as you can see, when the clock is asleep, if you unplug it and leave it sitting there, it is still uncompensated. The reason for that is that my test failed to take into account one parameter of the clock, which is its operating temperature. Although Nixie tubes are quite efficient, they do emit a small amount of heat regardless. So the internal of the clock body does generate a small amount of heat and operate at above ambient temperature. So if I was doing my test to figure if the clock was asleep, and it was on before that. If I unplugged it, it would cool back down, and I believe this temperature change has been messing with my oscillator I use for timekeeping and threw off my ability to compensate it. So the clock right now is not compensated for running when it is unplugged, but as it's just a software error, I can compensate it. I just need to adjust my testing procedures. The next test I did on it was to determine the viewability of the clock face. Now what I mean by that is, if you remember way back at the beginning, I said that Nixie tubes are made up of a stack of digits. Now because of this, some digits are further back in the tube and some digits are further forward. Now this is a diagram I made for the Nixie tubes I'm using specifically. The digit order depends widely on whatever tube you use. But for my tubes, the 1 is the furthest back and the 6 is the furthest in the front. What my concern was is that if the clock is showing 1s, like for example if it was 11 a.m. in 11 minutes and 11 seconds, that is theoretically the most restricted time of the clock. It would be the hardest to see. So I was unsure if how big of an effect this stack of digits would have on the viewability of the clock. So I conducted this test where I would place myself half a meter away from the clock and match my eye level to the height of the clock face, so I wouldn't be staring down at it. And I set the clock onto a protractor and rotated it along this leading edge of the clock face. So if I rotated counterclockwise, I would continue to rotate it until the digits became obscured and illegible, and that angle is known as alpha, and then I just rotated it clockwise and got another angle known as beta. Now the sum of these two angles is the total of my viewing range for the clock face. So my results of it, as you can see, if I was displaying the time 11:11:11, I have a viewing angle of 105 degrees. But if I was, I know I said earlier that Nixie tubes, the 6 is the furthest in the front, but having a clock that shows all 6s is not, that would never actually happen in real life. But the next highest digits I can use is 23, 56, 56. This is theoretically the most viewable time. And the result there I got was 112 degrees. So yes, my hypothesis was correct. The viewability of the clock does decrease depending on what time is being shown, but the effect is far less prominent than I expected, which is a wonderful result. So, to wrap up, having seen how the clock operates, or why the clock is designed the way it has, how it's wired, how it functions, I can say that right now the clock operates exactly as expected. Excuse me. The clock operates exactly as expected. The results of the timekeeping has been very acceptable, minus the one bug with the testing procedures needing to be adjusted to fully flesh it out. And throughout this entire project, the clock has remained entirely on budget, only requiring about $225 of my allotted $270, so I'm pleased with that. And there are several subtle viewing experiences with the clock that tend to be a lot more pleasurable than I thought. Some being the front-to-back movement of the digits as the clock counts, or being the subtle flickering of the colons. That'll come up here later in a second. And then lastly, yes, the minor timekeeping inaccuracy when it is unplugged, but that is to be resolved. Yeah, and I have my references here for what I worked with. So, getting on to the demonstration of the clock face, we will go into There we go. Oh, focused already. Sweet.
So this is the Nixie tube clock here. Now, as you might be able to see it here on the side, but this last digit here, ooh, wrong finger, that one, how that one moves up to a 6, which is the furthest in the front, and then that 1 slowly moves further back into the tube where it's harder to see. That's the effect I was talking about. But overall here on the front, you can see the clock face. And then along the right-hand side, you can see the user interface. I don't know why that got darker. But I have my set and select buttons for actually changing the time on the clock. Lastly, on the rear, it's hard to see because it's black plastic, but that's where my power input jack and on-off switch are. So if I were to set the time of the clock, I would press and hold, it says there, press and hold for approximately 2 seconds to set the time. So if I do that, you will see the clock will cease keeping time, and the moment I let go of the button, the colons will begin to pulse. So in this mode, this is what I was talking about in the coding flowchart, where after I press and hold the button, now it's toggled its system mode. So it's gone from time keep to time set. Those are the only operation modes it has. So in this mode, you can see underneath that first 0, there's a dot. That is actually the decimal point of the tube. That's one of the reasons I chose these tubes in particular, because they have decimal points. By pressing the select button again, I can cycle the position of that decimal point. And then by pressing the set button, I can set the value of that tube. So I can simply run through here and set the time of each digit individually. So, and once I have my time set and I know what I would like, I can simply go back to press and hold the select button again. And once I do that, the clock will pick right on up and go back to keeping time exactly where it left off. So now to showcase the timekeeping accuracy of the clock, I can't necessarily leave it here for 6 hours and say, hey, look, it's only 800 milliseconds off. So I prepared in advance. Get this up here. I prepared in advance the time-lapse footage that was recorded actually when I was performing that test that said it was only 800 milliseconds off. So if I start this video here, this was recorded over the span of 6 hours, and it's been sped up to approximately 1.5 minutes. So I'll tell you here, this is my reference clock, which is an online available, is a publicly accessible, online, government-controlled atomic clock. You can access it anywhere at www.time.gov. It's really fun. You never realize how many clocks are completely out of whack until you see it. This bar here is referencing my laptop's clock itself. So when it says that my clock is 71 milliseconds off per second, that is my laptop itself. This is the actual time as referenced from the atomic clock. And how I mentioned earlier about some aspects of the clock being kind of pleasurable, this is one of them. The subtle flickering of the colons is quite a joy. So, this test concludes at, I believe, 4:28 was when this test ran. If you noticed, I started this test at 10:33, so this video doesn't run exactly 6 hours. It's slightly less than, because I was taking that video at the beginning and end that I said earlier. So here you can see, even after running for 6 hours, it's right on the bat, not an issue. So that concludes my demonstrations of the clock face, or of the Nixie tube clock. Thank you very much. And do I have any questions?
Take us to the schematic. Which schematic, right?
There's a lot of them.
How about page 1 of 4?
Page 1. All
Yep.
right. Yep.
You talked, and I thought that you explained as well, actually, you talked about the need to have D1 and D2 in the circuit. What type of diode are you using there?
Those are specially chosen low dropout or low voltage drop Schottky diodes. The reason for that is because the microcontroller is configured with a brownout detector, and it will cease operation of the microcontroller if the voltage drops below 1.8. So since the battery is nominally 3 volts, I'm losing whatever voltage drop is on D2 before the microcontroller sees any voltage. So in order to extend the usable voltage range of the button cell battery, I want to get as low a voltage drop as possible on that diode. I believe these ones only have 200 millivolts when forward biased.
So how did you specially select them?
Parameters on DigiKey, hoping for the best.
Oh,
So they're not individually selected, see what you're saying specifically?
Oh, I
Yeah,
know, I
yeah.
see what you mean, yes.
I
did
imagine
look
you buy
for-
1,000 and going, nope.
Yeah.
yeah,
No,
that's good to clarify.
that serial number of diodes across the line are specified. I think they're 180 to
So
220.
you selected the proper device to the specification.
Correct.
Which is called engineering.
That's right. So you didn't really hope for the best, you actually.
Yeah, that's true.
Okay.
Well, I think I hope for the best when I'm checking to see what's in stock on DigiKey. I think that's
that's what
that's the scariest part.
I got the impression you hoped for the best that they would work.
Yeah, I did.
But I knew you better than that too. So you talked about the specific type of diode that D1 and D2 are. What function do they play here, and what would you name these diodes based on their function, not based on the type of diode that you ordered from DigiKey, but how you are using them here?
I don't know if this is the correct terminology, but I am using D1 and D2 to isolate the battery's voltage from VCC. Because if I didn't have D1, the battery would supply voltage to the entire 5-volt rail, so I would power shift registers, everything else in the circuit that doesn't need to be on when the clock is unplugged. And if I didn't have D2, then I would be throwing 5 volts into a 3-volt cell, which probably wouldn't be very happy.
And you explained that very well, and I'm just wondering, could you summarize the function of these two diodes in 2 words? Based on function.
Probably, I want to say voltage isolation, but I think that's the only term that comes to mind.
Those are our steering diodes, because what they're doing is a steering diode, what it does is it actually redirects current from its normal path to a different path, or from a different path.
I haven't heard of that
Yeah,
term.
so that's what they are, that's what they're actually.
Steering
Yeah,
diode.
so what you explained very well, by the way, is that function. Yeah.
All right, thank you.
What kind of battery is that?
A SR or CR 2032 button cell.
So what kind of protection do you have for overcharging it?
It does not charge, or it doesn't just. Oh, I see what you mean for like over discharge.
No, overcharge.
Overcharge shouldn't be getting charged, unless we're talking about like leakage current from the diode.
Oh, I see what you're saying. So it's just a regular.
Regular-
It's not a secondary source, it's a primary source.
Oh, I don't recall.
Secondary-
That
You
terminology.
remember
Battery?
primary and secondary storage?
Oh, right, yes, now I remember. Yeah,
From
that,
circuits?
that
Yeah.
battery is not rechargeable. It is in a holster inside the inside the enclosure.
I thought you were trying to recharge it.
Oh, no.
Honestly,
Uh,
all right.
Then the steering diodes would not be working
No,
in the
that's
way
right,
that you
it
explained it,
was
so.
a stupid assumption on my part. While we're here, well, actually not this one. you did something else here, I wanted the next
No,
slide.
I think you can go to the next slide.
Next slide.
I was interested in, C8, C9, C25, C26, and C10, and C21.
Yes.
Where did you get all of those, or how did you come up with getting all of those? I'm just curious.
C8 and C21 are electrolytic capacitors that are recommended as per the data sheet of that microcontroller. And C9, 25, 26, and 10 are decoupling capacitors that were put in there because I felt like it would need them.
What, decouple what?
That's the problem. So, I know that the U3 is analog, so I was worried about getting in too much noise from the switching regulator U2. So I've been kind of fighting with trying to make sure I didn't get too much noise anywhere in the circuit. It's the heart of
over
the
there.
switching regulator.
I do have that.
Yeah, go ahead.
Yes, by all means, go.
I'm thinking that you're not using a filter for the boost converter there.
That's what C6 is here on the far right. I just have a singular. I wasn't too concerned of noise coming out of the 190 volts because the Nixie tubes really don't have much influence on noise. They're not very sensitive to it at all.
So what's, besides, I don't know, I'm just, all those capacitors there, besides C8 and C21, which are probably doing the job of what you think everything there was doing.
Yeah.
And the reality is all of that extra capacitance there, if anything, is hindering your ability for U3 to do anything. Because all you've done is really add a lot of impedance to that. And then the plus 5 volts that's coming out of that, that's feeding, assuming that, that U2 and everything else, now it's seeing a whole bunch of impedance there that it needs to be corrected for also. And, you know, we do have the mantra, make sure you have decoupling capacitors, make sure, but I think this year, you guys have kind of put a little bit too much of the magic,
There's not
Justin,
any
yeah.
concerns that you're saying that haven't already come to mind. Like, it doesn't take anyone else to see that this kind of does seem a little strange, seeing so many
Because
capacitors.
for me is, again, who does the AZ 1117, who's the manufacturer? Go see them and see what they have to say. They built it, and if they're typically just saying, hey, C8 and C21 are what you're supposed to use, and by the way, these are the reasons for these, well, unless you have a significant problem, there is a lot about decoupling capacitors and that, but you can put too much too. Because you can go the other way, because all these decoupling capacitors are trying to prevent impedance issues from inductance,
Right.
right? How big's your board and how long is a trace from the plus 5 volts to the U2 feed, and then, how much inductance is really that? And if you put way too much capacitance, well, then you're just swinging the problem to the other side of the axis, but it's still the same problem. And then, again, you're right, 190 volts on tubes, it's probably not a big thing for visual, we're not gonna see any, so you get the right answer there, but I think you get the wrong answer at U3.
No, yeah, I'll,
I felt like they should be there, isn't engineering, right?
No.
yeah, no, I agree on that.
Yeah.
I will double check the data sheet for the 1117 and see what it,
Because I'll go a further step, I'll say, how come you picked 100 nano, 10 nano, why'd you pick those values? And I know probably your answer is going to be, you don't have to answer it, because I know, it's going to be when I go out there and I look at decoupling caps, those are the numbers they tell you to put in. But there's actually not a formula, but there's a calculation that you can find the real values of decoupling caps to what the size they're supposed to be. for the situation you're in. And I think in this case here, that's what would have applied there. It wouldn't have been a, well, here's a typical value, because that's probably where you got those numbers, right? You go online,
The 100 nanos were a generic value chosen, and then I had the 10 nanos recommended to me due to the noise from the switching of the microcontroller.
but then it's not a decoupling cap if it's dealing with noise. That's the other thing you guys did. Decoupling caps don't deal with noise. Okay, that's a filter. Okay, that's kind of what C6 is doing there. Okay,
What do decoupling caps handle?
They're to provide a, oh, excuse me. They're to provide a source for transient currents before,
From where?
caused by what?
no, not really certain, for the circuit.
It's typically on the device that you're trying to prevent the transient noise from getting into. Because that's actually the device that's causing the transient noise. You seem to be concerned about, for example, what's coming at 12 volts and what's going out to the 5 volts. The reality is decoupling caps for this thing would be cause U3 would be internal to the U3. The switching of U3 would require decoupling caps on the input. And whatever's at the 5 volts connected to that end, the issues of that would require the decoupling caps of C6, or C26, C10 on that device.
Oh,
Decoupling
I
caps are
see.
never on an output, they're always on an input,
I see.
and they're pertinent to the device at the point there. That's what they're trying to solve, the issues of internal switching and the taking up of energy based on a high impedance line, right, a relatively high impedance line. So in your case, because here's the other thing, when you studied filters last year, what's required to build a filter?
Resistor and capacitor.
Where's the resistor? In all your filtering you're accomplishing there, where's the resistor?
I see what you mean.
There's not a filter to be, there's not a resistor to be seen, and there's not a filter to be seen because of that. Okay? So, yep.
All right. I'll make note of these for future revisions.
Yes.
Well, that's the version 2 though.
Oh, I bought so many Nixie tubes, I'm making at least 3 more clocks.
Great
All right,
work. Good
thank
presentation.
you. thank you very much. We are just having a few last minute technical delays here. We're almost up to the next presentation with Darcy here. So I just again want to thank everybody for being here, either virtually or physically, and to just remind everybody that you know, we do this every year. We've had a very long history of doing this. I know that I've been an instructor here at the college for over 20 years, and it's been going on for way more than that, because I was a student here in '87, and I did my presentation then. So it's a pretty long history, and we think we put out a really great product in our students. And for those of you that are here from first year, this is what you get to look forward to next year. And you know, it's a lot of work, but it is, in the end, it is fulfilling, and it opens a lot of doors. And for possible employers in the crowd and on stream, well, we have these students available right now. They're waiting for to apply to the jobs and hopefully get a really good career start in electronics. So I think Darcy's got everything squared off there.
I think so.
Excellent. So Darcy's he's gonna talk to us about his oscilloscope clock.
All right, so good afternoon. My name is Darcy Hickey. I am in the EET industrial program, and my project is the oscilloscope clock. So you may have noticed from Mac's desktop background, oscilloscope drawing is basically put an oscilloscope in XY mode and supply the right signals to it. You can produce pretty much any sort of shape on the screen. And how that's typically done is by like a software that will convert an image or even a video into an audio file, and then you put like the left channel on one input and the right channel on the other input. And for my project, I wanted to replicate something like that, but with circuitry, so it would just be running on its own, not off of a computer. So for my main objectives for my project, I wanted it to be able to produce an image of some kind. I wanted that image to be able to move, so it would be constantly redrawing it. It had to be some sort of user interactability, so it could be controlled, and hopefully it should do something useful, something practical too. So that's why an analog clock was chosen as the thing that it's drawing. So here's kind of a simplified concept for it. So the image of the analog clock, it has the hands, it has some lines around the outside in place of numbers, and it has a circle. So, and my idea was, because the circle doesn't change, that can be drawn separately, because your hands have to be drawn by the microcontroller, because that's what's calculating the position and keeping the time and whatnot. But I found out you can produce a circle on an oscilloscope if you have a sine and a cos wave, or like two sine waves that are 90 degrees apart. So what I did, I had that be created by a separate part in the circuit. And then, so that circle gets drawn, it actually gets drawn a few hundred times. And then that switch will switch, and then the hands and the lines will all get drawn, and it'll switch back. Basically, that switch goes fast enough that all the elements of the clock will stay persistent on the screen. So I could have done it, at first I considered having it in more parts, because really only the hands have to move. So if you had something that drew all the lines, that would be even simpler, but ultimately the component count for that would have just been way too high, it would have been too complicated. So this is the circuit for the quadrature oscillator. That's the part that produces the sine and cos waves. And basically it's two LF356 op amps connected together, so they're oscillating. and the frequency it puts out is around, I think, 150 kilohertz, and it doesn't really matter what the frequency is, it just has to be high enough that circle is drawn several times so it remains persistent on the screen. And these are set up so the resistors were chosen that it would be an output of +4 to -4 volts, because I decided that when it's going to be displayed on the screen, it's going to be displayed at 1 volt per division, and that oscilloscope screen is 8 divisions high. So the microcontroller, that's drawing essentially all of the straight lines, and how it's doing that is with these R2R ladders connected to ports B and D, and I chose, because it has to create like an analog voltage. So I chose this approach because it was really quick. You could just load a value into port B, and that's I guess, the analog equivalent of that value would appear right on the output of that. And I made them 7 bits because that gives us a 128 by 128 grid to draw in. And that way there's 8 bits on each of those ports, so if one of those pins happens to break, you could just easily use another one. But because the microcontroller, it's all running at 5 volts, so those two R2R ladders that are producing your analog voltage, those only go up to 5 volts. So they go 0 to 5 volts. The overall display is going to be -4 to +4. So it essentially has to be shifted downwards and then amplified. So there's these 2 summing amplifiers connected to, there's 2 of these, and they essentially add -2.5 around. That's that value was adjustable, so you can move the clock face around to line it up, and they multiply it with a gain of -3, and that gain being negative just means it draws from, or it counts from right to left, but you can compensate for that in the software. And for the switches that effectively merge the 2 parts together, I use these ICs, these DG419s. And basically, those were really convenient because you can have like V plus and V minus, so you can have it just like the voltage in and out could be whatever level you needed it to. I think I have mine hooked up to +15 and -15. And then the VL, which sets the logic level, that's on 5 volts. So that is being controlled by the output of this. So this 555 timer, it just produces a square wave that alternates 0 to 5 volts. So it has a frequency, I think, of around 500, and that essentially switches back and forth to determine what part of the clock is being drawn, the circle or the rest of it. And I should have mentioned, I probably could have done it all just with the IC. The reason I decided not to was because the IC can only draw one thing at a time. So the longer its loop is, the more things it has to draw, the less visible each one is going to be. So it'll flicker more, it'll be harder to see, and there's still a bit of flickering visible in my finished clock, but it's still, I think it looks all right. So this is the main program. Basically, it has 2 modes. So if the switch on the front is high, then it's in set mode. Set disables timer 1. Timer 1 is the main 1-second timer that updates the clock every second. And when that is disabled, it's going to be reading the inputs from the 2 buttons to increment the hands by either 1 hour or 1 minute. Or if it's in run mode, that timer is going to be counting every second. it's not going to be reading the buttons, and it's just going to be drawing the face, finding the positions of the hands, and drawing the hands. And my goal was with this was to keep the loop as short as possible, because every second that it's not drawing something, it's like the screen is fading, so you have to essentially keep constantly redrawing it so it's visible. So the line drawing function kind of makes up the bulk of the code. It's based on something called Bresnam's line drawing algorithm. And I won't get into the full math with that, but basically, to draw a point, it finds you put in the coordinates, in like X and Y coordinates, it sets those to registers B and D, and then it will wait for about 1 nanosecond just so that little spot on the screen lights up. Then to draw a line, you just need to have a loop that will increment X or Y to move that point across. So when you're drawing a diagonal line that has a slope between 0 and 1, because this is kind of, it's on like a 128 by 128 pixel grid. So essentially, sometimes it will just increment, like if you're going a horizontal line, you just increment X until you reach the X position of the end point. If you're drawing a vertical line, you do the same with Y. But if you're drawing a diagonal line, you would have to increment X at every step, but only increment Y some of the time. So it uses this this equation that I don't have on here. It was kind of, I didn't want to get into it for time, but use this equation to determine if the point immediately to the right, or if the point 1 up and 1 to the right is closest to the actual line. Essentially, that version of it was only useful for drawing lines from left to right with slopes between 0 and 1. So I had to kind of modify it so that if it was a slope greater than 1, it would go based on the Y coordinate. So it would update Y every time, and then it would update X only when the point 1 up and 1 to the right was closer. So this was the kind of the main flow chart for the line drawing function. It's kind of hard to follow, but it first determines what the slope of the line is, if it's greater than or less than 1. And it does that by comparing the difference in X coordinates and the difference in Y coordinates between the start and finish points. And it would start at X0, Y0, which is the start point. Then it would run what's called the decision variable, which determines if the point up and to the right is closer. And just the convenient thing about why this function was chosen is it didn't require any floating point variables. It can all be done with integers. So it compares that, and it also looks at if the end point is greater or less than the start point. So that determines if it should be counting up or counting down, essentially. And with this kind of full version of the function, you're able to draw a line that starts at any point on the grid and that ends at any point on the grid. So it's really convenient for, you can draw pretty much anything, and it also makes drawing or calculating the position of the hands really convenient. Because all you need to do, because each hand, there's 3 hands, hours, minutes, and seconds, and they're each stored in 2 variables of angle and length. So first they get converted into radians just for the math library that I was using required that. And then take the sine find the x position of the end point of the hand, take the sine of the angle, multiply by length, and add 64 because all of the hands start at the center of the screen, which is 64, 64. And then for the y position, you just do the same with the cosine. And that essentially gives you the start and end points for the hands. So that line drawing algorithm, that line drawing function can connect those points. So yeah, there's kind of a problem with it. It's not too accurate. I ran it for 12 hours and it lost over a minute. So the reason why that is, if you notice, the time that it loses isn't consistent either. It could lose like 3 seconds in 2 hours, or it could lose 10. And the reason why that is because all the timers are based on the internal oscillator of the ATmega. So I kind of assumed that that would be 1 megahertz, or at least something close to it. But it turns out it varies quite a bit. So if I were to do this again, I would definitely use an external oscillator for that. But other than that, it still does most of what I wanted it to do. It can draw something, it has it move, and it can be controlled by a user. Yeah, like I said, the accuracy is not great. It's not really practical as a clock, but I think kind of due to the very nature of it, it has to be hooked up to an oscilloscope, so it's not going to be it was never really meant to be useful. Some other improvements that could be made. I had a lot of trouble with the PCB design, getting the footprints of everything right and getting the PCB to fit in the case. So I know I'm a bit under time. Should I move on to the demonstration?
So talk about your PCB for a minute. It's one of the things you ran into.
Yeah, so the main problem with the PCB was that I made the holes for some of the components too small. So that involved a lot of re-drilling holes and manually reshaping the leads on the components, so that was a bit time consuming. It's definitely not a mistake that I make again. Well, I guess I'll move on to the demonstration. I just remembered there was something I forgot to mention. Right, this was a bit that I forgot. When it's going through the main program, when it is in set mode and the button is pressed, there's another timer called timer 0 that just goes for like around 200 milliseconds. And what that essentially is, whenever it receives an input, it starts that timer, and it doesn't check any other inputs until that timer finishes. And the reason I included that was when you hold down a button, it's just going to start moving. The hands are just going to start moving, and when you release it, it's going to be hard to get it to stay in the spot where you want it. And so essentially with that timer, when you hold the button down, the hands would just move in steps. So that makes it a lot easier to set the correct time. How do I get the document camera?
Use the internal camera application. You search for it.
Okay. Okay, and then how do I change to the other camera? Okay, there we go.
Find it?
Yeah, now how do I put that on the screen?
Should slide to the left. I think I had it set up last.
Yeah, okay, there we go. Okay, so now to the demonstration. The scope does take a few seconds to warm up. Okay, there it is. So you can, there we go. Yeah, that's flickering a lot on the camera. As you can see, it's in set mode right now. So if I hold down the hour button, that will move in steps, that moves 30 degrees. If I hold down the minute button, that will move by 3 degrees, and it also moves the hour hand slightly. And then if I switch it to run mode, the second hand appears. And when that second hand makes a full rotation around, then the other hands will update as well.
Can you set it, why don't you set it to the precise time for us?
All right. It is a 2:51. So put the hour to after 1. Put the minute to 51. Start.
Maybe one more hour, isn't it?
Yeah, that's 1:51.
That's
Oh,
what
right.
I'm doing,
Okay. I don't know if you want to watch that for a minute to see if the other hands will update. But
yeah. Oh, yeah, it's kind of, maybe not a minute, but
yeah.
Where's the second hand?
kind of neat to see it work.
Right. It does look a lot better in person. The camera doesn't,
Yeah, I can
doesn't
see
capture
it.
it that well. Yeah. All right, so any questions?
You should actually turn the scope over, maybe people can see, because same here, I see on the side, it looks a lot
Right,
better.
I wanted to be able to set up the camera for it.
That's all right, like I know everybody kind of saw there, but it,
Everyone see that?
Yeah, we can still see it. I mean, it's smaller, but we can see it, yeah.
yeah, no, looks great.
Kind of surprising the variability in the mega clock.
Yeah, that was something I should have, I guess, checked beforehand, because that would have been,
How would you know? The only way to find it is by trying to monitor accuracy over an interval. Right?
yeah, and it's accurate enough that if you timed it for an hour, you wouldn't notice, or if you timed it for like 30 minutes, you probably wouldn't notice any difference. But I should have just measured the frequency of that before I even started, and then if I decided to use like an external oscillator, that would be a lot more accurate.
So let's talk about that then.
Let's talk about, yeah, you got some questions?
Well, yeah, he's talking about oscillators, okay?
Yeah.
So you use the internal oscillator
Yeah.
at 1 megahertz. So why wasn't it very accurate? Accurate or precise?
I guess neither, because it was set to 1 megahertz. The actual measured frequency was ranged between 948 kilohertz to 948.4.
So is that accuracy or precision?
Which would be precision.
Precision is resolution.
I guess it would be accuracy then.
There you go. So it was to the precision you wanted, it just wouldn't stay there, right?
Right.
So that's accuracy. So why did it vary that much? And why should that not have surprised you?
I guess it's not, the internal oscillator isn't really made for precision timekeeping.
Yeah, what's the technology they use?
It's an RC oscillator, I believe,
So what do they mean by an RC oscillator?
resistor and capacitor.
Yeah, so it uses charge, discharge of a
Yeah.
capacitor, right?
So I suppose if the voltage of the chip wasn't exactly right, that
That could be
oscillator would
issue,
also be
but-
different.
capacitors and resistors are notoriously variable too over thermal variations, aging, all kinds of things, right? So, yeah, it's not considered to be a very good timekeeper, right?
Right.
An external oscillator, what would have been the advantage of that? Because you could have just taken that RC, did the same thing externally, and it wouldn't have gotten any better.
No, I could have used like a crystal oscillator.
So why is that more stable?
I know they're more precise, they're more,
Accuracy.
yeah,
They have maybe a better resolution, but that's not usually why.
but they will generally always produce the same frequency.
Why?
I'm not really sure, I haven't looked into how the crystal oscillator would work.
Well, that's something you probably want to look into as a follow-up, right?
Yeah.
Okay. Yeah, right on.
What about, I mean, you built this project, you talked to us a little bit about some of the challenges you had. What about the type of display that is being used here? You must have had to learn something about that. What kind of display are you interfacing to here?
On the oscilloscope?
Yeah.
I'm not really sure what to call it.
But will this circuit that you build, this project that you built, work with any oscilloscope?
It will, it won't look as good though.
Okay, so let's get to the root of that. So why? Like, first of all, you don't know what type, this is a CRT display,
Right.
okay? You know what that stands for?
Cathode ray tube?
It's a cathode ray tube. Very good, so you did know.
Yeah, I just
Okay.
couldn't think of it at the time.
Okay, so in regards to a cathode ray tube, what's going on inside? How does it actually cause this display to occur?
There's a beam that's shot at the screen that lights up the phosphors.
Uh-huh,
What kind of beam?
yeah.
Electron? So with a digital oscilloscope, it wouldn't have the same phosphors, it wouldn't have the persistence. So you'd see it would be a lot fainter and the parts would flicker in and out.
Right,
What is persistent?
yeah, let's talk about that.
Well, because, it's still going there?
Yeah.
So, that's being drawn essentially one line at a time, but because it stays lit up, you can see them all at once.
So how long does it have to stay
Yeah, how long?
lit up?
I don't have an exact figure for that.
You mentioned flicker, right? And it does flicker a little bit.
We can see the flicker from here, yeah.
So there is a limit. There's a limit based on the hardware. But what's the other tool that has a limit?
I guess the human eye as well.
And do you know what the limit for the human eye is?
Can't remember it at the moment.
It's about 40 hertz. Anything under 40 hertz, we see flicker. Anything above 40 hertz goes away.
So I think if I just changed around some of the circuit for like that switches it back and forth, I could probably reduce that flicker.
What's your switching rate now?
I believe it's at like 200 hertz. That's
200 hertz, yeah. But see, you may be switching back and forth at 200 hertz, but you may not be drawing on the screen as fast
Right.
as that, right? Plus, the persistence of the scope, and we'll go back to that, the phosphor, how long it stays lit. Do you know what the values are for that particular scope?
no, I don't.
Because that's not variable, right? You're stuck with that, right?
Right.
If you took another scope, you'd be stuck with whatever value that has, right? Exactly. Whereas a digital scope, we have artificial persistence.
Yeah, what do we have there? That's a different type of display now, isn't it? What do we have? In the lab, if we hook this up to a TDS 2024B, what's going on in that scope?
So with the digital scopes, at least with the one I tested it on, your only options are a persistence of 0 or 1 second. So with 0, it doesn't all get drawn, and with 1 second, it's all there, but you'll see a motion blur on the second hand.
And is that a factor of the display? Or what's causing that?
That would be, I guess, the artificial persistence.
That's being done in the programming aspect, right?
Yeah.
Which scope only has 0 and 1? Not the one in the lab.
No.
Those have very low.
I thought the ones in the digital ones in the lab did, I'm not sure.
Oh, there's a lot more variability than
Yeah,
that.
there's more,
Yeah.
for sure.
So, let's take this another step further then. You had the camera here, this camera, displaying on the projector, which is shining an
Right.
image on the wall, okay? Display, camera display, what's going on there? How come we're seeing the flicker in a different way then?
Well, I'm guessing this little document camera probably doesn't have too high of a frame rate.
Right, so the frame rate of the camera has an effect too, doesn't it?
Yeah.
So if you had to do this again, what would you check before you came into the room and to present here?
Well, I guess I'd see if I could make the, because there was a bit in the code where I could alter the speed at which it draws things. So maybe I could try to change that to match the camera speed, so it would look better.
Or you could select a camera that has adjustable frame rate, and maybe setting the frame rate such that it's optimized for your project too would help.
Right.
Actually, I think we go to code for that.
Okay, let's look at the code.
I have a question.
I
Bring
didn't,
up that little snippet of code you had for the algorithm there. The one you talked about in your,
1 second.
or you should close that window.
I can't seem to find my cursor.
Yeah, all over the place.
It's probably on the other screen. Yeah, so it's on the other screen.
The mouse doesn't want to stay connected?
Oh,
There it is.
There it is.
That's there.
Okay. What was that? So,
Show that, you had a snippet of code here. Around where the algorithm was there.
this? Nope, I didn't figure that?
I hit F5. Shift F5, sorry.
Nope.
Is that already PowerPoint that's in there? All right, that's fine.
Okay.
So, again, just to paraphrase a little bit, you said that the interesting part of this was that these functions here was that it doesn't use float, only integers, okay? So before we go into the code, what's the benefit of that?
It reduces the likelihood for errors, because sometimes you add floats together and the result isn't what you'd expect.
Sure, yeah, that's right, floats can't express the whole range of values. What else is an issue with floats?
They use more memory.
Much more memory, and therefore, what do you do for the speed of your programming, your process?
It takes longer to calculate with
Because you
them.
gotta manipulate, right? So in your case over here, if I look at this, you have draw hand and the degree to radian. So, again, you said no floats, only integers, well, I noticed that one of the things that drawhand takes in is the variable angle, which is a float. And then it takes in integer length. And inside of there, I would assume that sin f means sinus, sin on a float, right?
So
And coast float, so those are float operations, right?
when I said there was no floats, that was just for the line drawing function, so there is floats used here,
Okay,
but this essentially just takes in the angle and length and then puts out the two coordinates that can be used by the line drawing function.
okay, so draw line would be the function that doesn't use. Like you call draw line after?
Yeah,
So that would be the function that doesn't use floats.
correct.
Okay, I misunderstood then, okay? But here's an interesting part of this. You have integer x over there equal to sine f of angle. Angle is a float times length, which is an integer, plus 64, which again will also be an integer. You are expecting to store in x an integer value, but you're performing float calculations on float variables. So what's happening there? Right, because x, in the end, you need it to be integer to pass the draw line,
Yes.
right? But look carefully, you're declaring x to be an integer, and then you're performing a float operation, I'm assuming sin f is float, okay, on an angle, which is on the variable angle, which is definitely float, okay? So the outcome is going to be stored in x, and it's going to be stored in x as an integer, because you declared it that way, otherwise it would, the compiler would say, that ain't gonna happen, okay? So, what do you think's happening there?
So, I assumed it would just be converted into an integer. Was there something else I was supposed to do for that?
Well, it is being, and it is being because there's a mechanism there that's called type promotion. I don't know if you remember that or not when you had your intro to programming. There was which is basically there's a hierarchy of types, and if you can go up to the next level in the hierarchy, you're safe to go. But you're lucky it does that in MPLab on the compiler that works with MPLab, okay, XC8. If it didn't have that, you would have a whole bunch of errors is what would have happened, okay? You would have to, by hand, manually, make sure that happens. Okay. You would have to do what's called a type definition. Okay, so I was wondering if you took that into you consider that or not.
I hadn't really considered that. I just knew that doing it this way would work in MP Labs.
Well, you got lucky, right?
Yeah.
Again. Had you been going the other way, float x equals, it wouldn't have worked, because the hierarchy doesn't work in that direction, okay? It would have given you an error, okay? My last question for this, how wide, or how many bits is x in your memory?
It's X.
In memory. It's an int,
It's an int.
so how many bits?
It could have been something shorter than an int.
Well,
Because
if
it's
you wanted it shorter, what would you have declared it?
a char,
The char, which is how many bits?
255,
No,
128.
no, that's very wide.
How many bit?
How many bits? So it's usually one bit, 8 bits, 16.
Oh, right, so, the char is 8 bits,
8 bits. How wide is an int?
16.
16.
So I could have used.
Oh, wait, let's finish that answer. 16 on the 328. Right? It depends on the platform. A char is always 8 bits because it's based on ASCII. But int, long int, short int, all those, depends on the platform. What other format were you taught instead of using int? Do you remember?
int
Int what?
8
Underscore t,
t,
right?
right?
And what was particular about those?
They're unsigned.
They're unsigned, but you could have done an int 8 underscore t if you wanted signed. What else was particular about those? How long is an int 8 underscore t?
8 bits.
Where?
Anywheres?
Always. Always. No matter what the platform, int 8 underscore t, it's an integer, 8-bit, signed. No matter what the platform, that's why we use that, okay? In this case here, it works for you, and it's 16 bits, and maybe you need 16 bits, maybe you don't, I don't know, okay? But if you bring that int to another platform, you might discover that int isn't 16, it may be 32, it might be 64.
Okay.
Okay? And you want to upgrade this to something that has a processor that's faster, has less flicker rate, things like that.
Yeah, and I realized kind of later on, but I didn't want to risk going back and changing things.
Well, you know, that would have been as simple as a
Yeah.
search and replace.
But those ints could have been chars because all of the coordinates just range from 0 to 128.
There you go. So there you have it, right? Or they could have been in 8 underscore t, right?
Right.
You int 8 underscore t, which would have been short, that's okay. Did you?
I didn't have any further questions on the code.
No, I thought you wanted to go to,
Did you want to do
schematic.
the schematic or?
Well, if you want to,
I thought you might. Well, I-
Bring up the schematic.
Yeah, we could bring up the schematic.
Which one?
the overall one or something?
The overall, yeah.
I didn't have it overall, I just had it in segments.
It's not there.
Oh, you know what, bring the one with the R2R ladder. I want
Yeah,
that one.
okay, yeah.
So bravo for using the R2R ladder, but the R2R ladder should have the, you should have the summing amps along with it, right? They kind of walk hand in hand.
Right, they are right next to each other. I just
Yeah, no, but I mean on the slides, they
Yeah.
belong to me, because what are they performing as a function?
They're converting the digital value into an analog value.
Yeah, but not just the R2R, right? The R2R and the summing amplifier,
yeah.
right, do that. So my question actually was, I was glad to see what you have there. My question really was though, why not just go buy a DAC or two and stick it at the output of there? Because you were talking about all these lovely little switch chips and ICs and that. And I thought, well, that was great. He built an R2R ladder DAC, and then he went and bought this specialty chip for the switching in that. Why not save yourself a little bit of hassle here and use a DAC kit? What would have been the advantage of using an IC with a DAC on it instead?
Well, it would have been less components, it would have been more compact, easier.
Sure, what else? One more thing. Which may explain a little bit of your jitter on your screen there.
It would have been less pins on the microcontroller, I don't think that's what you were.
Yeah, that's true, but that's not really. Those resistors are 12 or 13 or 17 or whatever they are there.
Yeah.
What's their precision, their accuracy, sorry?
5%?
They're 5%, so that means that R17 being 100K is 100K plus or minus 5%.
Yeah.
And they're more likely on the outside of the 5%, right?
Right.
They're not, there's probably not a resistor in there that's the 100K.
Right.
Statistically speaking, and the way they do it, there's not a resistor there. To make an A to, or a D to A that is really high accuracy needs what kind of resistor is there?
More precise ones, like
Not precise, accurate.
accurate.
Yeah. Higher accuracy, right? Okay, so no matter what you did, even if you went about a 1%, Okay, they'd only be as good as whatever your resistor values are for accuracy, right? Okay. If you bought a D to A though, it would tell you the D to A is accurate to this amount. And the advantage they would have over you is they're not selecting individual components, they're building resistors on the substrate and they're going in with a laser and trimming them all up, right? So then what happens is as an output, that you would have gotten a much better accuracy for the amount of money you would have paid for them, right?
Right, but that would, because the accuracy of that would just determine essentially the size of the pixels on the screen, wouldn't it?
No, but it would make a difference between every pixel, every location voltage out would be precise or accurately in a location every time.
Right.
Whereas now, you could have an interval of, I don't know, I'm gonna make up a number here, of 1 volt, and the next one could be 1.2, the next one could be 0.9, the next one, right? It's gonna be dependent on your resistor values. So as you're going around your circle there, your vector links may vary and not land at the same spot every time,
Okay.
right? Make sense?
Yeah.
Okay. So again, I'm glad to see that because you now understand the internals of one type of D to A converter.
Right.
And, you know, but the reality is there's a shortcoming to doing that manually, and that's why we never do it manually, is because we can buy the device on the same substrate, and it's all thermally balanced, you know, so if one resistor doesn't get hotter than the other one, things like that, where this could easily happen, right? So it's much more stable and so on. Okay? So, but it's just funny that you were picking these ICs for specialty requirements down on the earth, but here you chose to build your own, which again, there's nothing wrong with it. It's just, the other thing you could have done is buy a Mega Family IC that has D-Days built into it too.
Nothing wrong with it, it makes for some great questions,
Yeah, it makes for good questions here.
which I think we're out of time now, right? Good.
Good job, great project. Hold on, Ron, before you,
Yep. Do you want to talk to the stream too?
might as well.
Yeah.
All right, so that's it for our presentations for today. It is now 3:15. So tomorrow morning we will start again at 8:30. So 8:30, the first presentation will start. So we invite back everybody that can make it, either physically or virtually, to watch the day 2 of our presentations. And again, we'll have some more really great projects to show to everyone. So please, if you can, by all means, please come either physically or virtually. Thank you. The first years I want to talk to you before you go. Really impressive.
Yeah.